Welcome to On the Metal, Tales from the Hardware Software Interface. I'm Brian Cantrell. With me, as always, is Jess Purcell. Hey, Jess.
Hey, Brian.
Joining us in the garage as well is our boss, Steve Tuck. Hey, Steve.
Thank you for having me.
All right. And Jess, you want to introduce who we've got in the garage today?
So today we have Jonathon Blow, who created The Witness and other games, and I played The Witness, so I'm actually a huge fan.
Nice. Jonathon, welcome to the garage.
Well, thanks. I did not create The Witness single-handedly. Of course, we had a team of people making that. It's actually a classic thing in the video game industry is like people like to identify things with one person when it's actually, it's hard. It's hard making those things, but I'm glad you played the game and hopefully got something out of it.
So, Jonathon, it's great to have you here because we've had a bunch of folks on here on the podcast who have spent their life at the hardware software interface delivering compute to other people. Mm-hmm. But you're actually using compute to deliver an actual experience to an end user. You got a different perspective.
Yeah.
But very much trying to use hardware. And, when you and I first met, one of the questions I asked you was, out of curiosity, how much hardware capacity would you use? And you told me, I will use anything. I will use as much as you give me. I've got use for, which I thought was really interesting.
Yeah, for sure. Yeah, video games have plenty of ideas about things that we would like to do that we don't know how to do yet. Unfortunately, a lot of those ideas, like the more concrete flavors of those ideas are all in the same direction, like visuals, what things look like, which is, I don't know, like if video games like have a body, like we've been working out the biceps for a long time because those make money easily or something.
Right.
But there's all sorts of other things too in game. Like if you look at games these days, there are a lot of areas that are not like directly the pixels on the screen that get underrepresented in terms of technical effort so far, like animation or something, or even audio, like the way audio processing happens. In a video game is usually relatively low tech compared to the graphic. We're starting to beef it up, right? But the thing that makes games so hard, right, is there are many, many, many different categories of work that all have to come together to make the final thing. And every one of those is indefinitely fractally complex if you get really serious about doing a good job at it, and then of course, that just means bad things in terms of your to-do list if you're trying to build one of these things, right?
Right. Well, it's interesting you said that about like the animation, for example, because I remember the Prince of Persia when I was a kid was just mind-blowing. Even though the graphics were simple, the animation was so amazing.
Well, so sometimes things are easy until they're not, right? So the thing about Prince of Persia was it's a 2D game. You're viewing it from the side, right? And the reason it was nicely animated was because it was one of the first games where the author actually cared about animation a great deal and had this idea, like let's actually draw out these things and get them into the game. But the technical job to be done back then by modern standards was relatively simple. Back then it was a little bit harder because less capable computers, so you had to work harder to get all these pixels on the screen and stuff. But you've got a 2D sprite and you're flipping through it, right? And you just make sure the content of that sprite is really good. That's like job number one. And then job number two is just sort of the timing of when things happen. You just try to make sure that's good, right? So now in a current game, you might have a character moving around in a 3D world, and so objects are 3D, so they're more complicated. They have a lot more degrees of freedom. You expect them to move, like different parts of an object to move separately. It's a very different thing from having a sprite with some data baked in that you're just flipping pages on, right? And in general, because of this increased complexity, you have more of an interaction between things in their environments, and you can't really get away with the same stuff anymore. So in Prince of Persia, I'm having a little bit of difficulty calling up exactly what the screen looks like. But in all games of this kind, you sort of treat the character as a box or something, right?
Yeah.
And you do collision with the environment by saying okay, does this box overlap with other boxes, for example? Some games would do pixel accurate collision detection, but sometimes you don't actually want that, right? I'm not sure exactly which one this game did, but either version of that is a relatively simple problem. In 3D, you can't really do that. for various reasons. But like if I'm walking around on the ground and there's like a tiny rock on the ground that's kind of sticking up and like I'm colliding with it and I can't go, it looks to a player like there's just some kind of invisible wall. Like
Right.
it feels terrible, right?
Right.
And so just the degree of work that you have to do is just a lot.
Interesting.
Different. I'm not explaining it well enough yet, but it would probably take like an hour to just explain that point.
And work from like computational work from.
Yeah. So, I mean, just taking something like let's detect a collision between something and its environment as an example, right? Back in old style computers, there were ways of accelerating that, even on home computers, right? Like I think the Atari, I never had like an Atari home computer.
You never?
But
Really? Wow.
No, I was a Commodore 64 TRS-80 guy.
Okay.
When I was in high school, which is not, compared to your previous guests, that's recent history.
You and I are of the same vintage. So
Yeah.
this I mean, but I did have an Atari 2600.
A 2600 I had, but I mean like the computers,
The
right?
800.
The 800
Yeah.
and whatever the other one was. Yeah. So those I believe had like collision registers you could query where you would draw a
interesting.
sprite and then you could ask what pixels of this sprite hit pixels of this other sprite or something, right? And that was a way of speeding up this kind of a problem, right?
Okay.
And that works fine if you're doing
The
something
Atari 800
simple.
had that. And
Something had that.
yeah, no, that's fine. Yeah, no. A friend of mine had the Atari 800. It was kind of an
Maybe actually the Commodore 64 had that. I don't know.
Yeah, right. No,
but that was it's just to say that was the scale of technical problem
Right.
at that time.
Interesting.
It was either box versus, people didn't even really do box versus box that much. It was either box versus extents or like sprite versus sprite. I think Commodore 64 did have that. This is showing you how much I remember. Like I programmed that thing for years. I don't remember even what it did. So, these days it's a very, very, very different problem. So first of all, before you're even going to collide something, you need to like have something, right? So like, let's say I have a person walking around like a lot of games do. How do you do that, right? Well, you could imagine, for example, and the earliest 3D games do this, you could example that much like you do sprites by having like a flip book of images, you could have like some poses of a person doing a walk and you somehow represent the geometry in all these poses and you flip through it, right? Very early 3D games, like Quake 1 did this, for example. It doesn't do it anymore, like modern, well, sort of. But anyway, that has a lot of drawbacks, right? Okay, so how do you represent the geometry? Well, you have points in space. So there's like a 3D coordinate for every vertex. And then you have what's called an index array, which is just like, let's define a bunch of triangles. Or back then we were all like, maybe you should have higher order primitives or something, but it's still triangles today mostly. So you say like, okay, these three vertices have a triangle and these three and these three and these three. And that tells you what the geometry is. And then, you can have some additional properties like, if we want to vary the color over the surface, we have this thing called a texture map. And then each vertex can have an additional 2 coordinates, which is like its positions in the 2D space of this image, right? And that allows you to sort of stretch an image over it, which looks too bad if you stretch it too much and stuff. And so you represent the geometry that way. And then, okay, how do we animate it? Well, playing back these sets of coordinates is A, it's a huge amount of data, and B, it has a lot of drawbacks, like it's ill-defined between frames. And if you try to just straightforwardly interpolate the frames, you get these weird, stretchy, claymation-looking guys all the time, which you don't usually want. And so we do this thing called skeletal animation, which is you start defining these things called bones, which are essentially, for people with a math background, they're like a linear transformation that maps one set of coordinates in 3D space to another one, and it varies over time. And so then you store the position and orientation of like the root of each bone, and that's something that you can interpolate over time. And then the coordinates attached to that will like rotate through space and stuff. Anyway, this is becoming a really long explanation, but that's just even to have the thing, right? The thing that used to be a sprite.
Right.
Now is this thing.
Right.
Which is like way more data and way more complicated to talk about. And we haven't even talked about rendering this efficiently, which by the way is not that easy, right? It doesn't sound like it would be hard, but it starts to get hard. And so then if you wanted to say like, is my arm going to collide with this table, right? Well, you need to start thinking about things like how accurate does that collision need to be for example, right? Is it good enough if I just represent around my hand with like a relatively conservative sphere that captures all the volume? And then if it comes close to the table, if there's a tiny gap down there, can I see that or not, right? In a first-person game, you might see it if the gap is big, but in a third-person game where the camera's way back, you maybe don't care about that, right? Hand against table is a weird example. It's not really something we would do in a game that much, but like character against a wall or something, right? But, and then you start saying, well, okay, so maybe I had these invisible boxes around all these bones that I was just talking about. So there's like one on my forearm and one on my wrist and one on my shoulder. And then, so a character might have 30 or 40 of these. They're animating all the time. And then I need to sort of do some geometric intersection operation to intersect the arm with the table, right? Except that's not good enough, because if my arm is moving fast, it might have gone through the table. Like it might have been above the table on one frame and below the table on another frame. So then you have to like do some kind of time interpolated collision operation or something, have some way to make sure that you don't skip that. And then the problem with all that is once you start doing math like this, it's hard to do that in a frame rate independent way.
Right.
So what if I'm running this thing on one platform and it's kind of slow and I'm getting like 20 frames per second, and someone else is running something at 240 frames per second, which is not an uncommon number. Like actual gaming monitors these days are 240 FPS. Does the thing that I programmed feel different or the same under those two conditions? Like the way that you might write a physics equation, for example, like just doing like a Newtonian, this thing is moving around and it's being affected by whatever, right? So you might update the position based on the velocity, right? Update the velocity based on the acceleration, and then apply some friction, like, it's in air or water, so we're going to multiply its velocity down. And then you can just imagine those are relatively straightforward steps that anyone who even hasn't done games could probably imagine how to do pretty easily. The problem is the behavior of that thing that you come up with will vary tremendously based on what your update rate is. And so then you have to start having a strategy for that. Like, do we start trying to make the math more serious and more frame rate independent? Do we use like a more serious numerical integrator, right? Let's not go into that, but it's not simple, right? And all of this is like to do the thing that you used to be able to get in hardware, like, this sprite overlaps this one or not, right? And so, yeah.
And then, so how much are you able to kind of use von Neumann computation for that versus, say, special purpose hardware or special purpose accelerators? I mean, how much of that? And I assume that boundary has shifted over time.
I mean, it's complicated, right? So in principle, as far as I know, okay, the main kind of acceleration that we might use today, right, is a typical consumer PC or a game console has a pretty serious GPU, right, graphics processor on it that probably has more transistors than the CPU, right?
Yes.
But it's set up to do a different kind of a job. I don't really think of it as non-von Neumann, right? It just wants to have a lot more threads working than a typical,
yes,
a typical CPU, right? Normally, if we were going to make a game, we don't really conceptualize things very differently if they're going to run on the GPU. Like we always could see how we could write them for the CPU and how we could write them for the GPU. That might change more over time.
Interesting.
As the model continues to diverge, right? But usually like GPU programming is more about doing annoying stuff to satisfy the arbitrary constraints that are set forth for you that involved in just talking to the GPU. So like I've got to feed it my data, and that has to be efficient.
Yeah.
And I have to get results back somehow, and that has to be efficient. And it's just, there's this really weird, right? CPU talking to GPU is slow. GPU talking back to CPU is slow. So once something goes there, like once something goes to Vegas, it stays in Vegas, right?
Right.
But then a lot of that is not necessarily hardware constraints. A lot of it is often like software constraints, like because the APIs didn't take that seriously enough or whatever. But then also, this is the one part of what I do that's still changing substantially rapidly over time, is like GPUs keep improving in their capabilities. So it's hard to like say anything definitive.
Right. The fact that we do have special purpose compute, I mean, to me, it's interesting because games have driven so much I mean, obviously, it drove us as kids, and I think it still drives kids in terms of it's their first exposure to computing. I think for most computer scientists, it's the first thing they write is a game at some level, right? I think that's still true. I don't know, Jess, is that true for you? I mean, I assume
Choose your own adventure games, the text little tuies.
Right, exactly. So, I mean, and then from the hardware perspective, we develop hardware to, I mean, you would not have, I mean, I think that deep learning cannot alone support the GPU, right? The GPU needed that kind of much broader use case of, I would assume.
I feel like what happened, and again, it's not my job to like analyze the business of these things, right? But I feel like what happened is that games launched GPUs and are the reason that we had GPUs. And like I said, games always want more computation, right? And that's why there was this race, because whoever made the faster GPU could show demonstrably better results. It wasn't just a number. It's like, look at the screen, dude.
It's like, this is better.
This is better,
right?
Yeah, and that happened for a number of years. But I feel like now the deep learning people and the Bitcoin miners,
certainly the Bitcoin miners,
you put those two sets of people together, and they're probably a lot bigger than the game market. I feel like, but I don't know for sure.
I don't know for sure either, because I feel like when certainly I think that we saw that the cryptocurrency mining was playing more of a role in that special purpose compute than anyone realized when it kind of disappeared, and all of a sudden it's like, wow, where did a lot of the demand disappeared? That demand so correlated to the kind of the price of various cryptocurrencies. I mean, it's kind of so. It's hard to know how this stuff is being used, right? I mean, it's like it's sold, but you don't actually know how people are necessarily using it.
I'm sure NVIDIA knows, right? This is like they.
Sometimes I feel it's hard, honestly, especially if things are going well. It can be hard to know how these things are being used. You know who's buying them roughly, but you actually don't know sometimes how these things are being used and if they're being used efficiently. And if they're, I mean, I think that's why it's always interesting when you actually get to, I mean, you're actually trying to connect what you can do in hardware to actually an end deliverable, as opposed to for its own sake.
You know, it's an interesting point. So I was just thinking, I just said, I'm sure NVIDIA knows, right?
Right.
So their most recent card was the NVIDIA 2080 Ti. Like a classic thing about video game hardware is like, it's just ridiculous strings of numbers and letters, right? That make no sense unless you've been following it. So their whole marketing for that was like, it has this capability to do onboard ray tracing, like RTX was their thing, right? And it's honestly, it's a little too early to try and do ray traced rendering in games. We do a different thing usually. You could maybe add it a little bit into scenes and get a little bit of a bonus, but it's a little early yet. But that's, the way this always works is you start and it's a little early, and then next generation it's less early, and then eventually it's the thing. So we're sort of on the leading edge of that, I think. But the point is that their marketing behind that card was this ray tracing thing, which like deep learning people don't care about and Bitcoin miners don't care about. That's just a game thing. So they must still think it's important.
Yes. I think that the consumer market drives more broad compute innovations than I think anyone really wants to talk about. I mean, I think it's a bit of an open question. The fact that we have been driven to more expensive processes at smaller and smaller feature sizes, how much of that has been driven by cell phones? How much of that has been driven by mobile? I mean, I think we need those broader markets, honestly, to drive it. And that's why I think it's particularly interesting about how, as someone who sits in that broader market, how you use these underlying compute resources. So you use the cell, or you were...
Yeah.
Can you talk about that? That's such an interesting kind of experiment that was performed.
Yeah. So the cell processor, we should probably talk about what it was, right? So there was this weird time, and again, this is my viewpoint of it as somebody who was not involved in the CPU world very directly.
Right.
But just, peripherally working on software and stuff. But we had this weird time where the way processors were... The way that it looked like was the best way to increase performance for general purpose processors was to give them deeper and deeper pipelines, right? Because they had to predict more, right? And that obviously starts eating a lot of power. It's expensive and all this. So people started looking at like what can we do if we take some of that die space that's being reserved for speculative execution, right?
Right.
And just try to do something more straightforward with it. And so the cell was an attempt to say, okay, for what we're paying to do all this stuff, you could have a number of like much faster, much tighter cores,
Simpler
right?
cores. Yeah.
Simpler. They'd have their own memory,
Right.
right? So they don't spend a lot of time waiting on memory, which is one of the reasons that you need speculative execution for.
Right. The
right?
memory wall. Right.
And so, we'll just do that. And then you'll write like little sub-programs that you kind of upload to these things, right? And run them. Well, DMA, right? It's like not over a network. Well, a project I did involve that. But, and the theory was, you write a bunch of tight loops, they go to these things, you run them, you get the results back, and then you sort of had a slower main CPU that was in order, right? So it didn't do anything speculative. The job of which was to put these results together.
Right.
Right. And they weren't the only people that did that. So
And when was this? This was like early 2000s, right? When is Cell?
So the consumer console that had the cell in it was the PlayStation 3, right? Which I don't even want to remember exactly what years. So the year, okay, when I was working on Cell was before it was actually out. The first time that was in 2003.
Okay,
I wanna
right.
say.
Yeah, right. That sounds right.
So we're talking like, PS3 generation was probably like 2004 to
and
2010 or something.
And we are kind of now in the late stage dementia of Dennard scaling. Dennard scaling is beginning to break down in 2003, right? We are still, because the 5 gigahertz part, the power 5 gigahertz part is kind of in there somewhere, right? It's basically 2005, I think, is when that, you're right in that point where people are realizing that just accelerating clock does not make sense.
Well, I think a lot of people, like I remember talking to my friends about this in like 2001 or 2000,
Right.
like on Intel CPUs, it was starting to look like clock speeds were going to level off back then. But other CPUs were probably pushing it further. But yeah, so and they weren't the only people who had this thought. So the Xbox 360, which was the competitor console for that generation, didn't do that. But they said like, look, instead of one fancy out of order core, we're going to have 3 in order cores, and you could have 3 cores, right? How could that possibly be bad, right? And the answer is Amdahl's law is why that's bad for both systems, right? And so something that would happen on the cell processor is just like, okay, first of all, it's actually a non-trivial problem to try to factor a program into these little tiny pieces that will go onto this coprocessor and run quickly. And
as an outsider looking in, I have to tell you that was my first impression of Cell when I saw it. I was like, wow, this would be hard to program.
Well,
because you got so many, you got to keep these units busy. Now all this kind of this scheduling task has been thrown back on the programmer of I've got to have these little channel programs, for lack of a better word, and I've got to shunt them out to these devices, and I want to keep them busy. And then how do I figure out what's actually happening where, when? I mean, it felt like it would need a lot of cognitive load.
But even to get to that problem is actually kind of hard.
Oh,
so here's the thing about video games, right? Like there's different classes of problems, right? There are problems that are called embarrassingly parallel, where it's just like, the data do not have much dependency on each other.
Right.
Right. And so that's a thing that you can factor out and put on the side, right? So games don't have that much that's embarrassingly parallel. Like most of what we do has very heavy data dependencies on each other.
Okay.
And this has a lot of, even just outside of like what CPU you try to run on, this has a lot of implications. Like, so when you go to computer school and they tell you how to program, that you should factor your programs in certain ways so that this doesn't talk to this module does not talk to this module, right? They don't know anything about each other. That like doesn't make that much sense on a game, because in some sense, games are about mixing things together and having the complexity come out on the screen in a delightful way, right? So like if you're generating sound effects, those sound effects
need to be connected.
Should know what things look like, right? Like it should know what the surface looks like and like how many dust particles are happening. And so like a game is like a giant nexus of information coming together. And so have fun factoring that onto your coprocessor, right?
Well, I kind of feel like with embarrassingly parallel problems, I think everyone kind of assumes that someone else must have them. because it's like the statelessness in Kubernetes, right, Justin? Where it's like, all right, I guess everyone else has got these stateless problems. My problems have got like this kind of gnarly state that is interwoven into everything. I have to say, like, I kind of, someone who, other than my kind of early forays into game programming as a kid, I've always kind of assumed that, like, well, I don't know, games must be embarrassingly parallel. But
so the reason GPUs are so successful is because the very tail end is embarrassingly parallel.
Right,
like by the time you're done setting everything up,
right,
and like all this complicated thing, we've managed to factor it so that the very last step where the pixels go on the screen, which involves actually quite a lot of math, right?
That
usually,
part,
not all the time, but usually the math for one pixel does not depend on the math for the neighboring pixel.
Right.
And so then you can go wide at the very end. But everything before that is not so easy.
Not so easy. Yeah, that is really interesting. It's actually a lot harder than, because when you got this interconnectedness, it's very hard to accelerate in hardware. I mean, it's like,
yeah.
All right. So Cell was an attempt to, how is that part of the reason that Cell struggled? Is because there was more interconnectedness than kind of folks realized, or?
I think that was one reason, but also,
and it was like Toshiba and IBM and Sony.
Yes.
Was that? Am I remembering that?
I believe those are the three
Powers,
companies.
right?
Yeah.
Okay. Yeah.
And so actually, my first exposure to Cell was I was doing a project for IBM with some friends, and we essentially wrote a whole game. So IBM wanted to put these into servers, right? Because that's what they know how to do.
Right.
And they were like, what? Part of the reason I think that Cell floundered is all this research went into building this hardware in the theory that it was going to be dominant because these coprocessors were so fast, which I guess makes sense. But nobody really had mapped out all the way to software of like, what actually is this for, right? And so they had weird stuff like, oh, you're going to have this in your refrigerator and it's going to be awesome. And like the Sony people, see, I know people at Sony, so they'll get mad if I bring up embarrassing things in the past, but they were saying things like, when you buy a PlayStation 3, it'll talk to your refrigerator to get more processing power, or it'll call your friend's PlayStation down the street to get more processing power.
That's nuts.
Right?
Yeah.
They were actually saying that publicly,
right.
but also whether or not that's technically feasible at the hardware level, right? Which, whatever. It doesn't make sense in terms of a game. Like in a game, you need to know how much processing power is available to decide what to do.
I can't is your fridge available now? Is it not available now? Like I don't want to. And also, can you imagine you beat me in that game because like my fridge, someone opened my fridge and I lost the computational power and my frame rate slowed down.
Now, to be fair to Sony, Microsoft said equally dumb stuff the next console generation. So whatever.
Right.
I'll just throw that in there.
Yeah, right. But no company's got a monopoly on saying dumb stuff for sure.
I think hardware people were in the mindset that like, look, we just know how to make this fast. And software people are lazy and stupid.
Yes.
And we'll just get them to do the right thing when the hardware comes out and it'll be great. Right.
Yeah.
Now there is a little bit of truth to that. I don't want to like slag on hardware people, right?
Right.
There's a certain way in which software people have been lazy. Yeah. And like are not that interested in knowing the details of the system underneath and all these things. And especially today, the difference between even knowing some basic high level details about what you're running on and not is like orders of magnitude difference in performance, right? And so this stuff really matters. And I could understand being a hardware person and being just kind of frustrating at that, right?
Yeah.
But the problem is if that's going to be your plan, you have to actually know. You have to actually map it out from beginning to end. What does this turn into when it's actual software? And nobody ever did that, right?
Right.
And so, you see today, nobody uses a cell processor for anything. Nobody uses a descendant of a cell processor for anything.
Right.
Because it just didn't work out, right?
The model didn't work, and I think largely for software reasons, right? I mean, it was just a very hard model to program to, it seems like.
Yeah.
And so you're working on this project for IBM. I mean, were you able to demonstrate any kind of win? I mean, was it?
No. Okay. So the idea, now I don't know. I don't know what's typically, this is a dead project from a long time ago, but some of it might be under NDA technically.
Yeah, okay. Okay.
But okay. So the point was.
All right. So if you're listening to this and you're getting uptight about Jonathan talking about the cell, just relax because I actually think that I think some of these efforts I think the cell is an important experiment. And I think learning from that experiment is also important.
Yeah, no, it is super, super important, right? Okay, so IBM was looking for like, what can we do with servers that use this, right? And I was kind of aimless at that time. Like I'd had my own, I'd started a company with somebody and that didn't work out after several painful years. And then I'd done like independent consulting for a while and I was kind of working on my own games on the side, but like not really. I was kind of drifting around and like, I just moved to New York, I guess, and I got hooked up with some people at IBM through some friends. And I had this meeting with a guy from IBM and I was like, sure, I'll figure out what you can do with a server. And I had no idea prior to that. And so I went home and slept on it and I came up with a plan, which is just actually, so all this complicated physics stuff that I was mentioning earlier, let's actually take that one step further because then it'll explain what this thing was, right? So I talked about maybe, your hand hitting a table or not, right? But in a world full of stuff, it's actually more complicated than that, right? So if you have a coffee cup on a box on the table and you bump the table, right? What happens, right? Well, the things on it jostle.
Right.
And so you have these kind of semi-free objects that are holding each other up and colliding with each other. And like if a box moves and my coffee cup tilts, but it's kind of got coffee in the bottom so it doesn't tilt too far, like all those physics computations are, they're complicated, right? and in more than one way. So one is it's challenging to program those in an ideal environment, right? But then suppose you have a multiplayer game, all right? And let's say it matters whether your coffee spills or not, because the point of the game is don't spill the coffee, right? Okay. Well, the way you would do a distributed system in the face of like internet latency and unreliable packet delivery and things like this is you would do what's called in games client-side prediction. It goes under different names in different disciplines, but it's like, okay, normally we would make most of our physics just cosmetic. So like if I blow something up, it's got these chunks that come out and bounce on the ground and roll around, but they don't really affect gameplay. And what the server does is it sends to all the players, oh, this thing blew up. And we all generate our chunks and they bounce around. But the problem is the thing that blew up is going to be in a slightly different position for all of us because we're not synchronized.
Right. And it doesn't matter. So for this purpose, it doesn't matter that you and I are seeing slightly different things.
Right. And so you get this butterfly effect, right? Where my chunk, bounced off that wall and then that wall and then hit the coffee cup, right? And your chunk didn't, right? And so the game design was always about, we'll start using this physics stuff, but it won't matter, right? And so I said, well, what if you make this cool game where the physics actually matters? You have two problems. One is the synchronization problem. Because of the butterfly effect, you need to have a central authority over what's actually happening, and that would be the server, right? And then another thing that happens in multiplayer games all the time is people want to cheat, right? And so you kind of need to have security over like what's happening. And all of that means that if you had a server that was able to do physics really fast, you would enable a kind of game that you simply cannot do with a client server architecture with a weaker server, right? In the traditional way. And so the goal was this thing is simulating physics all the time. And so we had this cool game design where like you had like giant robots walking around, like 5-story high, and you could like shoot joints of them and like the arm would fall off or whatever. I don't know. And it was a small project. So I did the sort of what we would call the game engine and the rendering. And my friend Ottman, who later went to Oculus. He went to Valve and then Oculus. I don't know if he's still there, but he did he wrote a physics engine from scratch to do all this complicated stuff that I was talking about, right? But not only that, but do it on the cell. But not just one cell, right? Because the IBM plan was you have the cell, 2 cells in a blade or something, and you start slapping the blades in there.
Yeah.
Right? And, well, how do they talk to each other? And the answer was 10 megabyte Ethernet or something. 10 megabit. What was it? I don't remember.
Yeah, it would be like 100 megabit, maybe.
I think it was InfiniBand or something. But it was like slow InfiniBand. There was like a 10 option and a 100 option, and they didn't want to do the 100 because that was expensive.
As opposed to the InfiniBand.
Yeah, I don't know. I wasn't paying that much attention to that.
Right.
But the point was,
it sucked.
So because of what I was talking about before about in games, everything affects everything else. Yeah. Right? So typically what you would have to do is say, okay, we're at time t. We want to go to time t plus delta t, right? Where delta t is like 1/60th of a second or something, right? And we've got a world full of all these objects that are able to physically interact. And the job of this server is to just grind the iron and figure out all this physics, right?
And get back to me.
And it's more physics than will happen on one cell or even on one blade, right? So you kind of have to distribute the computation every frame, right? But now you're like distributing it over a kind of a slow network and like fanning out the computations and saying, okay, work on this, and then getting the results back. And we actually worked it out of like, okay, even if there's no problems, right? Even if we feed all the data optimally and manage to partition it optimally and all that, like, what is our speed limit just due to like waiting for the bits to get over the wire
Right.
and waiting for the results to come back? And it was an appreciable portion of that frame time. But we might not have been aiming for 1/60th of a second. It might have been like, I think it was 10. But still, like when you need to do an entire job, 10 times a second, it's just a different world than where a lot of people live in.
And where the late results are useless.
Yeah.
Right. It's like if you can't get back to me within 100 milliseconds, whatever my frame is going to be, like just forget it because we need to move on to the next frame.
Yeah. And so that particular, I don't like we wrote our final report for IBM, right? And our report was, this is not good hardware to do what you want to do actually. And here's how, here's try to be helpful. Like here's how you could change it and whatever. But they didn't like that because, if they're paying you to do a project, they want you to tell them how good their thing is, right?
For sure.
Like that. And I've actually been in that scenario multiple times when I was like a consultant, where I would tell people that something is bad and that's not what they were hiring me for, right? And that caused tension.
Right. I'm sorry. You were hired to describe how great this was, not to actually.
Yeah.
I think we've all been there, to be honest.
We've all been there. Well, and I think it all depends on like, what do you title your report to? I remember talking to another technologist who was talking about, he had an internal report that was not received well, entitled Burn the Boats. I'm like, was it actually called Burn the Boats? Yes, it's actually called Burn the Boats. It's like, all right, well, it's,
Your baby is ugly.
Yeah, exactly. Like, kill all management. Why? What's wrong with this report? It's like, well, I don't know.
Yeah, this was not that bad, but it was like we were like, look, you need at least 10 times faster,
Interesting.
Ethernet on this. And then even if you had that, it's still not that good of an idea because so you start, if you're to try to solve the problem I just mentioned, of like we're waiting all this time just for the bits to go out and come back, right? Well, you could start engineering that, right? Like, why don't we start compressing the data on the way out and back? And why don't we get like super smart about like what we transmit? Or why don't we hold a lot of state on the individual blades, right? So like maybe this one is authoritative over a portion of the world. And then if somebody crosses some invisible border, we move it to another one. And then what happens if it's in the middle, right? Once you start doing that stuff, and we could have done some of that stuff and it would have helped, right? But so first of all, you start driving complexity through the roof, which like in some sense was not, like you were supposed to be doing it much easier. And so that's indicative that something didn't turn out how you thought.
Right. It seems that, part of the purpose of this was to make it, I assume, not just faster, but easier to write games. Because what are the challenges?
Well, okay. The history of games, it's weird because the history of games has been us getting more and more complicated and doing crazier stuff in order to do better stuff, right? But there's some point, there is a cost-benefit analysis that has to happen, right? Like, how crazy are you asking me to be for what benefit? And, to be honest, like it was my idea to do this kind of game, but like the idea of a physics-based game that could sort of only happen with a big iron server it's not that great of an idea. Maybe it would be if like physics was better. Like, even today in 2019, like game physics are kind of floaty and weird. And maybe somehow if you got a really high quality experience, it would be a really good idea. But like, it wasn't a super good idea, I guess. And then how much are you paying to do this not super good idea?
Right. Right. All right, we're going to take a quick break and then we'll be back with more Jonathon Blow on the Metal.
On the Metal is brought to you by Oxide Computer Company. Well, I got to tell you, the podcast has been more successful than I originally anticipated.
Hey, that's great.
Yeah, there's good news. Folks are liking the content. There has been some negative feedback, though.
What, from the podcast? The podcast is great. These interviews are amazing.
The podcasts themselves, folks are liking. I've gotten a couple emails specifically calling out the repetitive ad content that's driving them crazy.
We only recorded 3 ad rolls. I know, we got a lot of ad breaks.
They were reminding me in email about the fact that there's only been 3 ad rolls that they've had to hear again and again and again.
Oh my God, we're so sorry. I mean, it's a great podcast. We don't want to ruin it with repetitive ad rolls.
Yeah, so I think it's something we should keep an eye on.
Okay, so in the meantime, we should just tell people to go to oxide.computer, I guess?
Yeah, that's all we need to do.
All right, sign up from the mailing list, and then we'll just we'll shut up. And hey, if you got any feedback on the ads, definitely send that to us, right?
Sure, we're getting it.
All right, sounds good. Back to the show. All right, we're back with Jonathon Blow.
I could say one thing before the question for Hepburn. I did later. So I did 2 things on Cell, right? So that was one of them. And then the other one was a lot easier and more simple because there are some embarrassingly parallel problems in games still, again, because we managed to factor it. And one of them is like particle systems, which is like games, like I mentioned explosions before. So you might have chunks of thing in an explosion, but you'll also have just like lots of little like dust particles and smoke and whatever. And the way those tend to happen in games is with a system that just does a bunch of little billboards that are animated over time, and like they may have ways of interacting with the environment, but it's very constrained. So it's like it's like its own thing, right? And whenever you have something that's its own thing, you can optimize that and crank on it, right? And so,
but I think you're making an interesting point earlier that when you have something that it's its own thing, it's not necessarily that core to gameplay because part of the game is that interconnectedness is what makes the game interesting.
Yes. However, every once in a while we discover things that are exceptions to that. So like particles are great because you just have a lot of them and they really help things look cool, right? And we just found that. And,
but how much of that is wow, this game's a lot more fun versus this definitely looks better.
It's more the second one, right? But actually, even in the earlier days, those two were not as clearly differentiated. Like now, graphics are pretty good,
right?
But back then,
Because I watched the games my kids play, and they basically play the logical equivalent of Atari 2600 games. I mean, you know what I mean? It's like the games that are really captivate them are the games that are super simple but have great gameplay.
Yeah,
that aren't actually no particles.
Yeah, I mean,
maybe my kids are have a low bar for their own entertainment, which is something that I've always believed. So,
there's weird generational stuff that happened, right? So around the time of Minecraft, which may be one of the games that they play, I don't know. So Minecraft came out, and it was this super low res, super chunky, very pixely, both 3D and 2D, and everybody looks at that who is a professional game developer and says, "Oh, yucky graphics or whatever." But kids don't know that.
Right.
They don't know that we worked so hard to get away from the Atari 2600. They just think oh, that's a retro style or something, right?
Right.
And so it didn't have the negative association that it would have for somebody who spends all day trying to make things look nice, right? And so it's just fun. I'm sorry. Yeah.
I'm sorry. I'm a kid. I'm stupid. I don't know any better. It's just fun.
No, Minecraft is actually a reasonable game, though. I don't know what games you're talking about.
I think this is more like the games on their phone. They play basically these very simple arcade games that are very. I mean, they're definitely very precise in terms of what but they're very captivating for them. They're they play levels that their friends make and stuff like. I mean, it's interesting in just terms of the relative simplicity of this stuff. And, it's amazing to me also how much the kids still love these basic puzzle games, the kind of like the Tetris kind of.
Plus.
Yeah, exactly. Right. I mean, it's like the logical descendants of Tetris are still really captivating, even though they are. And just I think it emphasizes also that the gameplay is really important and that it's easy, especially with an abundance of hardware, to kind of do things that are cool. But do they actually result in a better game? I mean,
well, for some of them, I'm sure it's the more immersive the experience, the better the game for some people. And having dust come up and a sound effect associated with that is going to make it more immersive.
Yeah, there's definitely different ideas of what a game is, right? So somebody who plays Red Dead Redemption 2, which is one of these games that's trying to be very high graphical fidelity and make a mood out of that and all this. probably isn't going to be playing the games that you're talking
Right,
about.
exactly,
Right?
yeah.
But that's maybe a good sign. It means that as an industry, we have a lot of different things that we could do
Interesting.
to talk to different people. But we ran over your question.
So I was going to go back to the butterfly effect because one question that I got in an interview for a job, and also one of my friends worked on Halo, so like I hear a lot about it, is like the distributed systems problem of like multiplayer games. So like say like I shoot Brian.
Hey, wait, that's your example? Like that's
No.
I mean, like,
Commonly come back to that.
And
can't
like,
you shoot a duck? Why do you need to shoot Brian?
because it's Halo.
All right, fine.
So like and Brian moves, or at least thinks that he moves out of the way. But like
Right.
on my screen, it looks like I hit him.
Yeah.
It's like solving that problem seems to be like, or at least from people that I've heard, solving that problem in a way that people can't cheat, which is also a problem that Halo had for a long time. It seems to be not like logic based. It's more like filling in the holes. Or I was wondering your take, honestly.
This is a complicated subject, behind which there is much history. So the fundamental problem again there is network latency, right? So even if everybody's getting perfect information all the time, which doesn't actually happen, but we're going to simplify and say that everybody's getting all the information about what happens when. It's just they're getting it with different amounts of time because I have a 10 ping to a server and my friend has 110 ping. That's like a tenth of a second difference, which sounds like a small amount of time, but it's actually quite large, at the speeds that people move in games. In a tenth of a second, you could be like a third of the way over on the screen. If you can be, completely non-intersecting with where your body was before that tenth of a second, right? And so these time spans matter actually a great deal. And so what do you do about that, right? And one reason why this is so complicated is because the answer to this question, or what you should be reasonably think about, has changed a lot over time, right? So my first professional game, actually, I started in the late 90s, 1996. And we were working really hard to do this kind of like live client server update stuff over 9600 baud modems, which was good. I mean, those were fast modems back then, man, 9600 baud. And again, we started having difficulties like how much time does it just take the bytes to go over the modem? That was like an appreciative percentage of the total latency, actually.
And you were trying to do effectively a first-person shooter.
Yeah, it was a little bit. It was like a sci-fi hover tank game, and so a lot of the weapons were indirect. It would be like I fire a missile at this guy, right? Which is one way of working around this problem, right?
Right. The weapons could take longer
because the missile's simulated on the server, and then the server decides what happens, and you eliminate this, right? But okay. So the problem is in these like first-person shooter games, people move pretty fast, and the server can't be authoritative over certain things, right? So for example, if I move the mouse, if that is, I tell the server how much I moved the mouse, and then the server decides how much I turned, and then it tells me how much I turned, and then I go that much. Even if the latency numbers sound really small to you, it's going to feel really bad.
Right, because you are now well within the domain of human perception.
And not even just perception, but like there's a way, like I forget the name of this, but there's a way that like humans use tools, right? Where like you consider it part of your body almost, right? So if you've got a hammer in your hand, you're not thinking that hard about the fact that you're using a hammer or you're holding a thing that's hitting a thing. You're like, oh, I'm just whacking this thing. There's some kind of like mental fusion that happens, right? And so games take advantage of that, actually, right? So if you're playing a keyboard and mouse game, I mean, Destiny is usually a gamepad, but mouse is a little bit harder, so I'm going to use that one. Somebody who's played these games a little bit doesn't think about the fact that they're controlling it, right? They're just moving their hand, and it's instinctual, right? And you kill the ability for that loop to happen.
It does not take much latency, I would imagine.
Yeah, not much. Well, and also variable amounts of latency, right?
Oh, interesting.
Because if it, like your brain can surprisingly adjust to a fixed amount of latency. It's not good,
right?
But you can,
right?
But when it's going up and down, you're like, it just feels terrible. It feels very frustrating, right?
Interesting.
So, well, what do you do, right? And so what people started doing, there were some famous presentations at conferences in like maybe late 90s, early 2000s, I forget, evangelizing different ways of solving this problem that I didn't personally like. So one of the things that you do, there's at least two different problems, right? So one is this problem of variable latency. People are seeing the world state with different, how do I explain all this?
There's a skew, right, in the way that they're seeing the world.
Yeah, I mean, okay, there's the fact that where I see things is by definition not where the server thinks they are, right? That's one thing. And then you have a second thing that's like, if two people take an action at about the same amount of time, and it takes a certain amount of time to travel to the server, and they're conflicting actions like who wins, right? That's a whole other thing. Usually we punt more on that second one than the first one. But anyway, so if we go back to the gun example, let's say you're standing there and then you duck behind a corner, right? In 100 milliseconds, but I shoot you before I see you duck behind the corner, right? We could even take the corner out of it. Let's just say you're in the open space, right? So what a lot of systems did that people started building was like, okay, we look at when the shoot message comes in, and we'll sort of go back in time to like,
interesting,
to when
it was actually fired.
When what we think your latency was, which by the way may not be a correct number, especially if it's fluctuating, right?
Okay,
we like go back in time that much and see if it looks like you were hittable from where I am, like not by exactly where I was pointing, because again, that won't totally make sense, but like in general, and then we'll count you as hit or not hit, right? But what that looks like from your side is like, we're in this intense gunfight and you get some shots off and you duck around the corner and maybe I hit you around the corner, right? Because you weren't around the corner before.
Right.
And maybe, and again, this is where it gets complicated. Like maybe at the time when the server needs to make the decision, you weren't around the corner yet according to it. Right? Because the server could decide, oh, you're behind the corner now, but you weren't before, but we're going to give you the benefit of the doubt or whatever. There's all sorts of weird heuristics.
Interesting.
The fact that there's all sorts of weird heuristics means that by definition, not everything is going to feel good. Something's going to go wrong, right? So it's kind of at its core not that solvable of a problem, right? But I mean, today internet is a lot better usually, right? And so you have some of these things like this thing Google is doing right now, the Stadia thing, which is like, look, the entire game just runs on a server and we just send you the pixels, right? Which it's not how I would do it. Let's put it that way.
That seems, the Stadia seems to be rather controversial. It seems to have,
but we can just use that to highlight the fact that like the assumptions there have to be very different. They have to be that like, oh, latency is going to be consistently very small, right? And so like what I always think about is like, okay, this kind of like, client side or client side prediction along with server side heuristics about managing these kind of events. I always, as a player, want to put a cap on that. I want to be able to say like, look, I don't want to play with anybody with a ping more than 50 milliseconds, right? So I just wish a game would like let me do that and like put that in the matchmaking or something. It's like, it's fine to have this kind of a thing, but like, let me control it or something. And nobody's done that. So maybe I have to do that at some point. I don't know.
Yeah. And you think about this is a hard problem because you are up against real physical limitations. I mean, you think about like a, 50 millisecond latency, which is like not, we can put physical constraints about how close that person is going to be to you. Right? I mean, it's like that person is not going to be in New York while you're in California. And yet it's a human perceptible, that has human perception consequences. So there are real physical consequences for how these kind of, and physical consequences for the game.
Yeah.
So it sounds like, take the Stadia thing. So why, first of all, actually, this kind of this correction of the past, which our brains do, right? Because your brain will correct for time that it didn't perceive.
Well, yeah.
So if you ever notice that, like you'll notice this when your eye falls on a clock with a second hand, and the second hand seems to be stopped, and then it starts moving again. That's because your brain has corrected for the time that your eye was in motion. So our brains do the same thing too, and we don't like it actually. It can have like these effects that are. So did you not like that approach? Because you said you disagreed with the.
Here's the thing. Like it comes down to why do you play games to begin with, and different kinds of games have different audiences that have different reasons for why they play games, and there's this weird what I would say conflict in the game design community where there are incentives to pull different directions, right? Okay, so a shooter game, right, is in theory about being better or worse at being able to do the shooty stuff, right? And to like win. It's a competitive kind of thing. It's like if I win, I'm probably better than you, mostly like in the same way that if sports teams win, whatever, one of them's better, right? And so it's playing that game is ostensibly to the people who are interested in it about building your skills at the game and working on it in some sense and getting better. And you know, there are some shooter games that are way more serious. So for example, there's a game called Counter-Strike on the PC. I guess they did console versions, but it's mostly PC game where it's like, it gets really serious, right? There are like world tournaments of like, you know, video game sports teams playing each other at this game all the time.
Right.
And it's like, it's a very fast and vicious game, right? And the skill level is very, very, very high, right? So like what a lot of people want to play this kind of shooter game for is for a more casual version of that, right? But if you're a company and you want to sell a thing to the most people, right? It's tempting, and I think this is true as well. Like a certain number of people are playing it for a different reason. They want to be like the fantasy of the cool army guy who like kicks ass, right? But maybe they don't care about being good at it.
Right.
Exactly.
Interesting.
Right. And if you include those people, you get a bigger audience, right?
Right.
And I'm not sure which group is actually bigger. I think most people would tell you that latter group was bigger, but I think that's kind of wrong. Like I think people like being competent, actually.
Yes.
Mostly.
Yeah.
Right.
Right.
And so I think that's undervalued. But the point is you'll make different design decisions depending on which game you think you're making, right? And so this design decision about like, let's give people the most smooth feeling, most comfortable experience at the cost of unfairness, essentially, right? Like maybe you got out of the way in time and you still got hit, right? That turns off people who are interested in competence to a certain degree because they get really good at the game. The more good you are at it,
The more injustice.
yeah, first of all, the more you see these things.
Right,
Like
right.
a new player might not notice that this is really happening, but after a while you're like, no, that was wrong, right?
Interesting.
And then also the more you feel you're being disrespected by the game. Because it's like, look, I'm putting in this effort and the freaking game is not even right. And it's just angering, right?
Interesting.
And so, yeah, I would feel that the right decision to make would be more in support of competence, like whatever that means. And I hope we go that way, but we haven't gone that way historically. Like, so for example, I would just say like, look, you know, like I said, we could have different matchmaking tranches or whatever according to connection quality. And, you know, if you have a not that good connection and you want to be good at the game, like how serious do you take this? Do you take it seriously enough to make sure that your Comcast connection isn't terrible or whatever? Or don't you? If you don't, that's fine, but you just can't play in the top thing, right?
Right.
And I would prefer that as opposed to like just pretending like you're having a fair and reasonable match when you can shoot somebody half a second ago. Like that doesn't make sense, you know?
Totally.
Interesting. So when I think getting to why games, because there is so much. I mean, there is such a wide. I think. Well, there are a lot of different games out there, but I feel that the ones that are popular with the broadest possible folks are not necessarily the ones where the industry focuses. Is that a fair assessment? I mean, it feels like that the industry focuses on a narrow tranche, maybe for economic reasons, maybe. I mean, God knows my kids have never paid for a game.
You know, there's almost not really one video game industry now.
Right.
You know,
Interesting.
there's the traditional one, which is the one that I live in, right? And all this stuff I was talking about physics and whatever is all from that one, right? And then there's like the iOS game industry,
Right.
which is like hopefully your kids are not playing the most exploitative games, but like a lot of these are like I think of them as just like pretending to be games in order to have a microtransaction button or something,
Right.
you know,
Oh,
or to
God,
show
yeah.
ads. And those are very different things because they're all about, you know, exploiting people's psychology in I would say unethical ways.
Yeah. Interesting. Yeah.
And really they're not usually very interesting as games because they're just kind of, they're only trying to be a game in as much as is necessary to get people to spend time in front of it and to engage the worst compulsions that they have. And so I actually have very little respect for that whole industry. Now, I don't know if this includes the kind of games you're talking about.
Yeah, no, but
are you talking about like the modern iterations of the classic SimCity?
Yeah.
Yeah, like Farmville.
Yeah.
Because like SimCity was great and it was, I think, productive and healthy, but some of the newer, maybe dumbed down versions of it do people sit in front of a screen just clicking all day.
Yeah, I mean, it's a weird thing, right? So SimCity and Farmville from a 30,000 foot view don't look that different. It's like you're kind of controlling this spatially laid out structure and building it up, right? But like SimCity is a creative activity that involves thoughtfulness and problem solving and skill. And Farmville is just about getting you to sit in front of the screen for as long as possible.
It's a slot machine, right?
They're two different things at a basic level. And I don't like that. And again, this makes people in my industry mad, when I just say it that bluntly, because it's like, look, I say it different ways at different times, but like, if you don't respect the player, if you're not trying to actually give them something, if you're purely entering this from a perspective of trying to take something from people and give them as little as possible. I mean, on the one sense, that's the optimization of capitalism, but in the other sense, that's very socially negative. And we recognize that as a society, right? And in fact, in other industries, we ban things sometimes with quite harsh legal penalties when they are seen as socially negative enough, right? And so, I'm not calling for banning those games right here, but like I certainly don't respect the people who work on them. Let me put it that way. That's how I feel about it.
I also feel that has their time come and gone to a certain degree? I feel like that there was a kind of a Farmville moment.
I mean,
period. It feels like that people are more aware of the kind of the exploitive nature of those games.
I think they're just, it feels like they're just prevalent. They're just different iterations of them, whether they are like a particular media star that has their own game now where you can go through a house and you can buy things if you build up enough points or pay for enough points. And
yeah, like kind of like with .com booms and busts, right? Or technology booms and busts.
Right.
There's been several waves of this. So there was like casual games on the PC, right? And then Facebook happened, and then somehow there was like all these games on Facebook, right? Which is where Farmville, I think, came from.
Right.
And then the smartphones happened, and so then you had the first wave of this stuff on the smartphones, and maybe now we're in the second or even third wave of like, sets of games that are all sort of doing the same thing that's like different from what prior generations of them did. So they do come and go like waves, but like new waves keep showing up.
Right.
The ocean doesn't run out of waves.
Right.
Do you have a favorite game that you've played? Like a game that kind of helped inform or drive your career in the game space?
There are a number of them, and it's an eclectic group. So when I was a kid on my Commodore 64, I liked the text adventures, like the Infocom text adventures. And my favorite one was a game called Trinity by Brian Moriarty, which was probably the most like literature, I would say, or the most that hit me in the right spot. It was sort of a science fiction premise where like World War III happens and you sort of manage to escape in this weird extra dimensional way. And then you're trying to prevent it from happening by going to all these historic times when like moments in the development of the atomic bomb were happening, for example, right? And so the end game, this is a little bit of a spoiler, but the end game happens.
This was an Infocom game?
Yes.
Oh, nice.
The end game happens like at the Trinity test site. It's like historically recreated and stuff. So,
cool.
Yeah, the Infocom games are available. I mean,
I'm gonna find it after this. I was like, I've made a mental note. I'm like gonna go.
That sounds fun.
Yeah, there's these sets. I think they're still called the Lost Treasures of Infocom.
Lost Treasures of Infocom. Yep.
I think you could buy it off Amazon or something, and they'll send you a box like with all the maps and like cool. Like those games always had little physical objects. Right?
Yeah, the ephemera were so great.
I think you also could get it on iOS. I wouldn't recommend that because typing on a touchscreen is terrible.
Yeah.
But I think in those cases they have like screenshots of it, or I don't know, of the little baubles. Yeah. Anyway, so that is very different from what I do today, but it affected me in a relatively deep way in terms of the way that I think about games. Like sometimes the way a creator does things, like you feel that and you keep that as opposed to the surface manifestations of whatever it is the thing that they made.
And
right?
did you, because, I was much older when I realized how they actually implemented that stuff in terms of like they had their own virtual machine. Infocom was a super interesting company.
It was a little wacky. Yeah. It's weird. Like I think of them as such a major part of my childhood and stuff, but that company wasn't even around for very long. It was like, I want to say like 4 years. It might not have even been that long.
Oh my God, that was, it just felt like a lot longer.
Things happened fast back then.
Yeah, it felt so seminal. I don't know.
Maybe that 4 years is incorrect. Don't, fact check me later. But yeah, in college, when I should have been studying computer science, I played a number of video games. I played some MUDs, which were the multiplayer text adventures back then. And but my favorite game was a game called NetTrek, which was actually made by students there, which was a client server. I would describe it as like playing football with Star Trek ships. Like, so you had like different classes of ships and you were trying to fly around, and it like updated very blinkily at 10 frames per second on Sun 360 workstations.
There you go.
The main things that we would play
right.
that on. Or Apollo workstations.
Right.
I don't know if you know those.
Yeah, I do definitely know Apollo because the Apollo lab had just been replaced by the Sun lab when I showed up at university. So they had just gotten rid of the Apollos, which
yeah.
Well, and so that's your first real exposure to networked games too, because we did not have, when you and I were growing up, I mean, the BBSs were not on a 2400 baud modem. It was not, I didn't play any kind of networked game.
There was weird stuff that was a little bit game-ish, but it was very asynchronous. Like I'll do a move and then log out, and you'll do a move tomorrow.
Right, it's like chess.
And I never really played those. They weren't very engaging.
So you discover networked games at school.
Yeah. And then my first company after school, I mean, I worked so after school, I did like a really boring enterprise software company for 6 months. No offense to the people I know from that time, but like it wasn't a thing. And then I went to, I got a contract at SGI, which was still a thing back then.
You bet.
And I ported this relatively famous game, Doom, to like this set-top box system that they had. Right?
Yeah.
And that was my first official
box,
professional.
Is this for the Orlando thing?
Yes.
Wow. There we go. That set-top box is amazing.
I don't know if I would say amazing without quotes around it.
It's amazing. Oh, it's amazing.
How do you know about this?
Well, so I felt like this was something that was well known at the time.
Because it was hardly deployed. It was deployed a little bit in Florida and a little bit in Japan, as far as I know.
And if I recall, it was classic SGI in that it was technically very interesting at a price point that was insane. I don't remember. I think that the box was going to be like $10,000 a box, and it's like, well, like no one's going to buy those. I mean, that's because they actually deployed them. It wasn't in Orlando, right? I believe so. Yeah, no, I felt like it was a famous folly by the time I arrived in Silicon Valley in 1996.
Well, and so toward the end of this project, like 1 or 2 months before my contract was over, all the relatively senior people all left to go to Netscape because Netscape was like poaching from everywhere. Right. And so that really it was like, oh my God, we were having a hard time on this project and now everybody quit.
Everyone just left. Yeah.
But so same problems seem to keep coming up, right? So like Doom was made to run on PCs, right? With local disk. And these set-top boxes didn't have local disk. They talked over Ethernet to a central server to get files, right? And that's fine if you want to read big files, but like Doom, it's got a thing called it was called a WAD file for Doom, but it's basically like a zip file or a package where you put a bunch of little pieces of data into one file, and it would, for a given level, it would look up an index of like, okay, which graphics do I need and which sounds do I need, and it would seek back and forth around this file. And of course, the API for this set-top box system like didn't have an efficient way to do that. It was like if you did a lot of small reads, each one was a round trip to the server and back, and like who knows. So I actually shipped, to the extent that this thing shipped, I wrote a server that like, you would like coalesce all your reads and send it to that thing, and it would like do all the reads and package them and send it back to you, which like my ideas of what was okay to ship in terms of software quality back then are very different from what they are today. And just, my level of experience is very different and stuff. So I'm kind of scared of whatever it is that I wrote to do that. Right. But that was officially it was a really weird thing because at first I was talking to other people in the group and I was like, look, we need to do this. It's just too slow. There's nothing I can do on the client side to make this faster.
Right.
With the API that you've given me. And they were like, it was staunch no. And then eventually it was like, oh, fine. Give us your server, we'll install it. So like, yeah, I don't know. It was weird.
And what was the graphics acceleration on hardware on that? Because I do feel that you can trace the NVIDIA origin story potentially through this project. Because the NVIDIA folks all came from SGI, right? It was all the Odyssey folks at SGI that quit.
Yeah,
and went to,
I'm not sure about that. It may have had I assume it had a graphics accelerator in it because it was SGI. I remember it could do like alpha blending and stuff. So there was definitely a thing where there was something at least doing fast compositing and probably some other graphics pipeline stuff. The thing is, my port of Doom didn't use any of that stuff because Doom was made for
the
systems that do not have that.
Yeah.
Pixel at a time.
Right.
And so, I was just making that work.
Right.
Which,
right.
It was just like, fill out the image and then call the thing that presents that image. So it's not actually particularly low level.
Right. Interesting. So, and actually, I ported Doom to QNX, which was a real-time operating system at about the same time.
Okay.
So
you know what I'm talking about.
Oh, definitely. Yeah. No, it was the WAD file definitely brings back memories.
Yeah. It wasn't that hard of a thing to port.
It was not actually. No, it was actually pretty,
which was great.
It was pretty cool.
Yeah.
And so I was sort of the 286 actually quite a bit. It was actually Wolfenstein Wolfenstein was the one that was and I'm sure you had the same, again, because we're roughly the same vintage. I mean, that was just eye-popping to have.
Oh, yeah.
I mean, all of a sudden, you were running on a 286 or a 386 SX or whatever it was, and all of a sudden you had what felt like a 3D game.
Yeah, it's mostly 3D.
It's mostly 3D, right?
Kind of. I mean, it came in steps, right? So Wolfenstein, is doing this, what we call 2.5D, where there's essentially a 2D map of the world, and then walls have heights or whatever, and you sort of fake it, right?
You fake it.
And in Wolfenstein, all the walls were sort of on, essentially on graph paper, right? They're all orthogonal to each other, and that means certain things are mathematically nice, so you don't have to think that hard if you're trying to figure out how to render it, right?
Right.
But even, it's weird, like earlier games had much lower performance pseudo 3D stuff. So like if you play the Ultima games or something, I don't know if you ever saw it, you'd be like in the dungeon and you hit like forward and it sort of redraws this dungeon thing that is just some white walls with a couple squares on it or whatever, right? And so you definitely could connect it to things that were earlier, but at the same time, it was sort of a qualitative jump in what was being done, right? And then Doom was even more. Doom was like not gridded. It was like free form.
Right. We're going to take another quick break. I want to come back and I want to talk some more Doom here. Back with more Jonathon Blow on the Metal.
On the Metal is brought to you by the Oxide Computer Company. Well, thought we had a bit of time to deal with this, but it sounds like the listeners are pretty restless.
Uh-oh. Is this about the ads?
Yes.
Oh, no.
The inbox is full.
Oh, boy.
They also have begun recording their own ads and sending them to us, requesting mercy from the repetitive ads that we've been subjecting them to.
Wait a minute. They're in such pain over the ads that they're sending us ads for Oxide?
Yeah. I picked one out. Have a listen. This is from listener Paul Guaz.
I'm getting really, really, really tired of listening to the same Oxide.computer ads every week, talking about how the Oxide Computer Company is going to make your on-premises infrastructure faster, more efficient, more secure, and just all around less painful. So much so, in fact, that I wrote and recorded this ad. Head on over to Oxide.computer to learn more and join their mailing list.
I think we should just do what Paul said.
Yeah, let's just follow his instructions.
Let's get back to the show. All right, we're back. So, Jonathon, you just ported Doom to SGI's doomed set-top box.
Yeah. I assume it never went anywhere, but I don't actually know.
I think the price point was debilitating. I think it was viewed as a folly, I think. It was a Silicon Valley company trying to enter consumer electronics, and in a way that backfired.
Yeah.
Was kind of how it was perceived. But I do think that some of that Although SGI was kind of coming apart at the seams at that point. They had a CFO with a Coke problem, among other things.
Exactly.
Oh, yeah.
Okay.
That was,
It doesn't sound good.
no, it was bad. Now, SGI.
Don't do that in your company.
No, we will not be doing that. We will not be doing that. SGI had, there was a hugely innovative company, but it was nuts.
Yeah, I don't know what happened because you sort of, like the world became so much about graphics and like they missed that. It's like they were in the earlier age of graphics and then they kind of missed a transition.
Yeah. Well, they didn't know what they wanted to be, whether they wanted to be an enterprise computing company or a graphics company. And remember, because they changed their name. They were Silicon Graphics and they changed their name to SGI.
Right, yes.
Which is one of these like corporate moves. You're just like, have head and hands. This is like when Sun changed the ticker symbol from Sun W to Java. You're just like, oh, God, no.
Sell.
Exactly. Thank you for just embarrassing every employee. Every employee just has their head in their hands. And oh, my God. And but I think that, as I recall, it was a bunch of the NVIDIA folks were all ex-SGI. I mean, I want to go
quite plausible.
Check that. But so what did you do after SGI?
I started a company with a friend. Here, actually, our first office was in Oakland.
There you go.
Downtown, there's this mall like at 12th Street. We had a little thing there.
And this is in the early 2000s. This is post.com.
No, this was 96.
Oh, wow. Okay.
Yeah, this is pre.com bust.
Bust.
And then, so this company lasted till like 2000, 2001.
Okay.
So we sort of saw the whole .com thing happening.
Right.
And
okay.
I was just like, I'm not doing that.
Right.
I'm doing my thing. And it was really difficult. So this turned out to be, well, first of all, we didn't really know anything about video games, right? We had no like experience, except I'd programmed games, I played them and stuff, but it would have helped to have somebody who had done things in the industry before, as opposed to us, which were just like, hey, let's start a game company. Okay, how hard could it be, right? But also it was, I'm convinced, the hardest time in history to start a video game company, like almost to the month, because previously games had been 2D, right? And now with, so 1996, beginning of 96 was when Quake Test came out, like when we were starting our company, right? Which was like basically fully running Quake, but without all the levels and stuff. They were just doing like a multiplayer beta to make sure all that worked. And so Quake was the first real, like, it wasn't actually the first like fully 3D game, but it was the first that like ran at high frame rates where like action-y things happened. And that just kind of changed the whole game industry. And so everybody had to do that now. Right. Problem is nobody really knew how to do that at many levels. So first of all, like we were saying, no graphics accelerators. So you had to draw every pixel on the screen. You had to do that really fast. And it just, a significant amount of math was required, right? All this, like the whole geometry situation was not quite as complicated as what I said at the beginning, but it almost, getting there. And just computers were still kind of slow. And so you really had to sweat. So like, so we were working on 486s in the beginning, maybe three, like we were working on 486s and we were hoping to ship for 386s also. Right. And so fortunately for us,
I mean, you think this is a 66 megahertz clock rate.
I mean,
on a 46,
sometimes it was that high.
So, right, exactly. Right, lower. I mean, it's like, you think about like the amount. I mean, that is running on like a RISC-V today.
Yeah.
Right. I mean, it's like in terms of the what you were doing, how little the horsepower is.
I don't know how to compare it honestly to anything today, but but also the thing that you do in games is you're trying to be ambitious. You're not trying to do the same thing that people already did. You're trying to push ahead. So we were trying to do like an open world where you could like drive your little hovering tank around all these mountains and stuff. And part of the secret of Quake was it was like indoors and very constrained, like visibly. So you didn't spend a lot of CPU to figure out what to render, right? So there was that. There was a great deal to learn. But okay, so here's the great thing about this time historically, is that the guys who worked on Quake, which was John Carmack, who I guess he was CTO at Oculus recently and now just quit to go do AI on his own. And Mike Abrash, who's a relatively well-regarded, famous person as well, were working really hard for a year and a half to figure out how to make this game possible, right? Or I guess the whole development was like a year and 9 months or something. again, fact check those. But like that, they then went to these conferences, right? For example, the Game Developers Conference in San Francisco, and said, here's exactly how we did this. Everybody else in the industry who we're ostensibly competing with, here is what we did to like get the geometry on the screen. And the most magical thing was the texture mapping loop that would go from pixel to pixel. And they said, here's our assembly language. Like anybody obviously could disassemble it, but like it was really weird because the inner loop that wrote each pixel, like Abrash figured out weird side effects of some of the x86 instructions that like weren't exactly the intended purpose, but when you strung them together, you could get some work that you wanted to happen. And yeah, so I spent a lot of time trying to do variants of that. So they had this 6-cycle thing, but of course you want to like add features and stuff. So you try to add cycles to your texture mapper, but not too many. And so And because you didn't have that many addressable registers back then, I'm sitting there programming in assembly and like, okay, we're going to use the base pointer as like a general register because we don't.
There you go.
And then that makes it really fun to debug, right?
Right, exactly. The classic reuse of the frame pointer. Oh my God, there's a special place in hell for people who reuse the frame pointer.
You had to because you couldn't.
I am looking forward to the room in hell where it's like, wait a minute, what are you doing here? Then you finally realize, like, wait a minute, we all reuse the frame pointer. That's why we're all, I know. No, it is. You had to. You do have to, but God, it makes it brutal to debug.
Yeah. And so that's what I was doing for a few years. And just, we didn't have business savvy. And also it was a weird time. So like we ended up signing our game with these companies that were going to try to be like, like cable TV channels, but like for the emerging internet. And the idea was they would provide low latency connections over your modem. And so we signed with this company called Total Entertainment Network that was based in San Francisco. And, we made some money off that contract, and that kept us alive at subsistence level for some amount of time. But eventually that whole market just like didn't happen. It didn't end up that people were paying subscription fees for good modem gaming, right? Because like what happened instead is just the more open internet happened. And, so if we had done something where it was like, we're selling our game directly over the internet, we might have actually succeeded, even though that was crazy. Like the idea of processing a credit card on the internet in 1996 was like not really hardly anybody did that.
And I see what you're saying about it being a tough time because it's like post-internet but pre-internet at the same time.
Yes.
It's like everyone knows the internet is here and no one has it yet.
Yeah.
Right. It was all dial up. It was super slow. It was, this is what you remember Boo.com.
They were ringing a bell, but I don't remember.
Were a retailer. They were going to be a streetwear retailer that had a super complicated Flash retail site when everyone only had 57K at best, and it was just like you had to wait for 15 minutes for the site to load. It's like, well, goodbye. And a retailer, same kind of thing. It's like you're at exactly the kind of wrong time.
Yeah, but so I worked hard for years and it was very sad a lot of the time, but it was really, it's a large part of where I learned how to program, right? I mean, I went to college so I programmed a lot at home, in high school and grade school on like, home computers. So I kind of got that. But then I went to computer science school and it was like, oh, so there's like actual formalisms behind some of these things, which I think was an important thing to learn, right? I actually dropped out of that eventually, like not soon enough. Like I had like one semester left, which is the stupidest thing. It's like, just stick around and do the last semester and get your degree, but I couldn't do it. I was not, But anyway.
I'm sure they'll let you finish it up though. You could probably give the commencement address.
Yeah, I don't like school. So I learned certain things there, right? But they're still not, like what you learn in school is not that practical. Like there's a mixture. Right. There's ideas. There's a lot of ideas about how you should program and how computers should work and all this. And some of them are right and some of them are actually pretty wrong. Yeah. And you have to kind of go learn which ones are right and which ones are wrong. And that's where I did that.
You have to have a very lab-intensive computer science curriculum for this exact reason.
Even then though, like that helps, right? But a lab project in school that you would do in one semester, like that's not the same as like I'm building a game from scratch with my bare hands for 4 years. Yeah. Like that's just different. And so we started a company at the hardest possible time, but I also feel like I'm like a programmer who was raised during wartime, and I look around today and I'm like, people can't really program today. Like it's because they weren't forced to in a sense. Like that's a little bit of a facetious way to say it. Like people can definitely program in the sense that they type in relatively uncareful things into a computer and then approximately the right thing happens in return. But it's like, it's not the same.
Well, no, I think you're right. Well, I think that in particular that the era of resource constraint seemed to have ended.
Well, okay, here's a magical thing about games is that we still had resource constraint. We still do today.
Right.
Because we're in competition with each other.
Right.
And because a lot of the platforms that we ship on are actually like fixed platforms. Like here's the CPU, here's the GPU, here's the memory. You know what all these things are. You know what the speed of all of them are, like a game console. And the people who make the game console have an interest in you being able to program it well.
Right.
And so you don't have these super thick abstracted APIs that you don't know what's going on. It's like, oh, you actually know when you call this function what the graphics processor is actually doing in response to that. If you actually care enough to dig into that, right? And so when I say a lot of people don't know how to program today, I kind of accept certain parts of video games from that. Now it's a big industry, and there's a spectrum of
this
what
is an
people
important
do.
point
But
in
like,
terms of like the resource utilization has immediate commercial value. So you do understand what the metal that's underneath you a lot better. You have to.
Yeah. And again, I'm in a weird space there because, my whole shtick, so there's large video game companies with hundreds or thousands of people, which is again, like, that's still a pipsqueak tiny thing compared to web companies, but like a giant, massive, hugely successful video game that makes billions of dollars, like Red Dead Redemption 2 or something. I mean, probably, I don't actually know the numbers on that game, but it would be typical for something like that to peak at 1,000 people. And that's just like toward the end when a lot of people jump on to try to finish it up.
Okay.
But like probably hundreds for most of development, right? Which
it's a lot of people.
It's a lot of people, but it's also not a lot of people compared to some companies, right?
Sure.
And so it's weird, right? It's a lot of people to try to coordinate when you're trying to be very precise about what you're doing, and when they're all somehow like hammering on the same spot, right? Because
right.
Yeah. I don't know, but those are the biggest game projects, right? But so my history is much, much, much smaller. So the game before The Witness that I did called Braid, like I did most of it, and then there's a guy, David Hellman, who drew the majority of the visuals, and then we had a few other people help out. But that shipped on the Xbox 360 in 2008, and it was competitive with other games that you could play. Like it wasn't competitive in the sense of like high budget production values, but in terms of being an interesting game that you could play that like looked nice,
fun.
And and it was successful on the platform, and like so that's kind of been my thing since then, is like doing a lot with a little, right? In terms of resources, and that's hard sometimes. It's but the weird thing about doing a lot with a little is because the things we're trying to do are ambitious, we are definitely very much in touch with reality of like what goes fast on computers, right? And most of the work that we do is about making things go fast, right? Ultimately, like even, so if we want to get some graphics on the screen, there's ways to do that are very abstracted, and there's ways to do that are very fast, and those are not the same way. In fact, they're very different from each other, right? And so we do the fast way, or we try to, in as much as that's possible. Sometimes it's too ill-defined, so if you're going to ship on a lot of different PCs with different GPUs, it gets harder to know what to do, right? But our deal is just we work pretty hard, and we try to be productive. And the way that I found to be productive, and this is a little bit paradoxical, especially for being on this podcast, is like you can't be that far from the CPU, but if you think every little CPU thing is super interesting and rat hole on doing the optimal job on that thing, you will never ship a large piece of software, right? And I've seen a lot of people do that. And so I've sort of been in this weird middle place where it's like, like for Braid on the Xbox 360, it was like, oh, particle system's slow. I should use some SIMD intrinsics to speed that up. So I spend like a month or two learning that and putting it in. And then I'm like, all right, it's fast enough. I got to move on, right? Because there's just so much to do.
Right.
Yeah.
It does. Well, but that's interesting.
And actually, in retrospect, I'm sure I could have done a much better job on that particle system with my current experience had I time traveled back. But like, so there's also this thing where computers today are just too complicated. A modern Intel, i7 dash whatever random string of digits you have, if you're going to try to actually understand what that's doing in response to your software, it's very difficult. Even using all the tools that Intel gives you, it's very unlike, for example, in the Quake days, where it was like, okay, a lot of the CPUs this is going to run on are Pentiums. It's got this like dual pumped thing.
Right.
So we could I forget what the terminology was,
Right,
but
the
like
R and V pipe, right?
you had
or is the R and U pipe?
I think of it as A
U
and B,
pipe.
but
What were the,
whatever.
Yeah, right.
But the point is, you'd issue some things for pipe A and then B,
Right,
and
right.
you'd move your instructions around, just to try to keep those balanced, right?
Right.
And but that was a thing where you understood what was going on, and now that's simply not even possible, really. Mostly, so the number one thing to understand in games, and we're reaching the point because things are so complicated that not that many game programmers understand it. But the number one thing is, don't miss your data cache, right?
Right.
Because you pay, again, it depends, but you pay hundreds of cycles for doing that.
Yeah.
And the absolute worst case is dependent pointer reads where okay,
Yeah.
I'm looking through this pointer to get this other pointer that what, and it doesn't matter how much speculative execution you have at that point.
Right.
Probably most of those cycles are not going to get filled, right?
Yeah.
And so the problem
It's
is
still the memory wall. Yeah.
yeah. And the thing is, most ideas of how to program, both the ones from academia and also the industry ones, which are kind of a different thing, but industry best practices, ways to program, all don't really contend with this reality yet. And so we in the games industry, we have various things. So data-oriented design, I don't know if you've heard of that.
No.
It's a thing. It was started by some people who are not me, but I think it's a good idea. And it's basically look, if you want your program to run well, you need to look at what the data transformations are and design for that, because that's by far the limiting factor on the processing you'll be able to do.
Yeah, interesting.
And by the way, when you do that, that doesn't look anything like object-oriented programming, for
Right.
example, because object-oriented is a totally different factoring that'll cause you to be very slow. But it also doesn't look like a lot of things that you learn in computer school. So in computer science class, they love telling you to allocate nodes all the time and have pointers between nodes. That's half of what you learn.
Right.
But it's suddenly we're in a world where that is very, very slow, right? But then maybe a lot of programmers don't need to care.
So I have to ask you.
Yeah.
I feel like this is a very on-brand question for me to ask you. So have you looked at Rust at all? Because I think
I have a little bit. I actually famously, I have a rant on YouTube for an hour about
nice.
Rust.
I'll have to go watch it.
Totally. Okay, so I don't know if you know this, right, about me. So I'm also making a programming language now to replace C++.
Ooh.
Because like I said, my shtick is doing a lot with a little. So
Yeah.
So building a game engine, which is, the thing that sort of runs the gameplay code and all that, is usually people wouldn't even do that these days. They would use licensed engines.
Yeah.
For both Braid and The Witness, we built our own things. But while I was building The Witness, I was C++, it's not really a good language to do this. When you're 5 years into a project, Witness took 6.5 years. When you're 5.5 years in, and you're just oh my God, this is such a slog. When are we going to be done with this? Right. Which, even if you're working on the most exciting thing you ever worked on, if you're doing it intensely for that long, it's hard,
That's
right?
a long time. Yeah.
And then to go in and feel like a lot of my time was being wasted by this stupid programming language.
By the language
right?
itself, yeah.
Yeah. Which by the way, is really the only option for us in that industry. There's good reasons why we use C++, but also it's a terrible language at this point. It used to be not so bad, but then the direction that they're taking C++ is less and less reality-based, I would say.
Okay, this is interesting. 'Cause my view is that C++ was terrible, and that people who, because I decided, C++ and I broke up in college, and I just decided we could never be together.
Yeah.
And people said, oh, it's gotten better, and C++ 11 and C++ 17, and I'm that's great for you. I can't go back to C++ because of the way that relationship broke up with me, which is C++ dragging all my stuff into the street and lighting it on fire.
Yeah.
It's we're definitely not getting back together.
I would say that C++ 11 added some good stuff.
Okay.
But after that,
It overshot.
And then the problem that C++ has is there's a lot of design mistakes in the past that they have to carry forward. And so everything new that gets added is hobbled by having to deal with all these other things, right? And so,
I mean, that's its origin story, right?
Yeah,
It is
exactly.
C++. I mean, the end, just the necessary compatibility with C. And it's like the comma operator. You can overload the comma operator. What does that mean? Nobody knows.
Certainly, if you do it, nobody's going to understand.
Nobody's going to understand it. It's got right to left evaluation. It's like, no good is going to happen from overloading the comma operator.
Yeah. So anyway, so that's the backdrop of all this. And,
Right.
and so I started making the language that I'm working on in like 2014 toward the end, but it wasn't a serious full-time thing until 2016, right? But so now we're building a game in a game engine that's a new engine because it's in the new language that is in development. And we're doing that full stack of things at once right now.
This is Jai, J-A-I? What is
Yeah.
Okay.
And so
do you pronounce it Jai? I'm sorry.
I tend not to pronounce it. It's a code name because one of my
you don't pronounce it. Like, you're the guy. You have to tell people how to say
so
it.
one of my pet peeves.
It's like you can't tell people to not pronounce it.
One of my pet peeves for decades, and it got worse once open source became this weird social thing.
Okay.
Right? Is like you go on Hacker News or even before that, you read some Usenet posting or some paper, and it's like everybody introduces their like project to you, and it's like whatever weird name, like Diamond Dust, : and then they tell you what the thing does.
Yeah.
And then you go check it out, and it kind of sucks, and it hasn't had that much work put into it, and it's maybe not that good of an idea in the first place, right? Most of the time. And it's like people put all their effort into the cool name and the idea that they're doing a project, and then putting it out in the world and getting people to sign up for their project that hasn't really had that much work put into it.
Yeah.
So I am doing things in the opposite way.
There you go. Okay.
This language
a name that
I've
is
been working
deliberately
on.
not pronounceable.
Well, it's not that it's not
No,
pronounceable. It's just that
sorry.
I don't use it because it's maybe not the real name.
Okay, got it. Fair enough.
And we haven't released this language to anybody, even though it's been in work for 5 years.
Okay.
It's been runnable for the whole time. It's been expanding in feature
that's
set and
really
reliability
interesting.
and all this. But like, so one of my beefs about open
You know
source
what I have
again.
to say, I also like about that is like I feel there is too much emphasis, especially in open source, on winning. And it's like my language needs to win.
Yeah.
And my database needs to win and my software needs to win. And it's like, actually, your software, if it's useful for you, it can just, I love the fact that you got this language that is usable, that you're using, that you haven't yet released.
Yeah. So I went to Berkeley, right? And there was this idea of the Berkeley approach versus the MIT approach back then, and that the Berkeley approach always wins, right? The MIT approach was you craft some beautiful jewel in your backyard or in your garage or something for many years and you make it perfect and then you release it. And the Berkeley approach was like, oh, you just kind of do something and you let people use it. Sort of like the minimum viable product that like web people do now.
Right.
And so that was considered to be like the right way to do things. But situations change. And I think we're now in a situation where everybody in the world is flooded by low quality software and everybody wishes that they had higher quality software. At least people who make software, I think, right? And so the amount of time that I like, so we're making a game. Games have a lot of things they want to do. A lot of those things are potentially stuff that a library could do of some kind, right? And so let's go out, whether it's, maybe to do some constructive solid geometry or like, text layout or something, right? There's a lot of different little subjobs, right? And so if I go on the internet, like what is the state of the art of what people out there are doing for this task, right? Very often I will find a number of things that claim to do the job. Some of them actually do it to an okay level and some don't. And a lot of them don't really work for like high stress situations. And a lot of them don't even like frickin' compile anywhere, right? And like just the amount of swimming through a sewer that I have to do to even figure out what is the thing that I should seriously consider to maybe do this job versus writing it myself.
Right.
That is a huge investment, time and energy investment, right? And then maybe I start using something and then I find out later that it doesn't do a very robust job of solving the problem, but it took me a month to figure that out, right? Because things were, that's how much investment I had to put in to get to the point where the problem was hard. And it's like, I've developed a very strong distaste for that. Like, I feel like if you put some source code out into the world and claim that people should check this cool thing out, and it's like not actually doing a good job at what it does, you're kind of creating an ecological disaster because of the scaling factor, right?
Yeah,
how many people are going to download? How many people are going to invest time in your thing before they figure out it's not actually good?
So the NPM ecosystem is going to be the canonical example of this problem for you, I imagine.
Sure, I have very little experience in that territory,
Oh, God, you should avoid it.
Sounds, I know about LeftPad and all that stuff.
Oh yeah, no, just from a psychological safety perspective, you should avoid the NPM ecosystem because it is the absolute very worst. I mean, don't you feel, Jess, that there's a spectrum, and I do think that and I think the Go ecosystem is probably meh. It's kind of in the middle
of good software.
If there are in the Node ecosystem, there are 15 things that do this task, none of them well.
Okay, that's
in the Go ecosystem. There are 6 things that do this task. Some of them okay.
Some of them forkable to make good.
Some for and
but I think that's just a testament of the fact that JavaScript is around longer.
I totally agree that JavaScript's core value is growth, is metastasis, and as a result, they want to make everyone be able to write a program, which I think is laudable at some level, but it means that there's a lot of garbage out there. It is, I have to say, is one of the things that, again, I know I'm being very on brand here, but it's one of the things I like about Rust is that it's so much harder to get something to work, and but in terms of the cognitive load, I mean, it forces you to have this the true cognitive load of your software. You have to absorb when you're developing it, as opposed to being able to just kind of poop it out.
Well, so I agree that that's good. The thing that I don't like so much about Rust and several other languages, the mission statement of Rust, broadly speaking, I think is very good, right?
Fast and safe.
Yes, we're gonna improve. Let me make it even more general. And who knows? Rust people might not agree with this restatement, but the broad thing that we need to work on is we need to make software work better. Generally, we need to make it more so that when you write a program, you know that it's correct, right? To a greater degree than today.
Yep.
Right. And it would be helpful to do that in ways that are not the ones that have been well trodden, because we kind of have seen those ways before. So for example, a garbage collect, like a Lisp variant or something, right? Is actually, it's safe in certain ways, but it's actually very unsafe in other ways, because Lisps, for example, were not traditionally statically type checked. And who realized that that's actually important, right? And so, Rust, I think, has a good set of ingredients there. The problem that I have with it is when I'm working on really hard stuff, I don't exactly know what I'm doing for a long time.
Right.
Yes. And so,
this is a fair criticism.
if the cost of experimentation is driven too high, it actually impairs my ability to get work done. Right.
Yeah, I think that's fair.
So my approach that we're doing in the language I'm working on is different. It's you have very, very, very extensive metaprogramming facilities, and you can use those to build your own correctness checking, right, for your program that you traditionally would have needed to make a compiler extension to do, which is that's pretty far away from what people do day to day, and they just don't end up doing it, even if they could have, right? And so what happens is your metaprogram gets information that normally would only be internal to the compiler. You get a message loop while you're compiling, and it's this declaration just compiled. It's a procedure. You get the full type, here's the types of the arguments, here's the types of the return value, here's the, this identifier maps to this other thing. And so you could start having house rules okay, so an example is.
So I have kind of the compile time, I have compile time logic that can enforce different kind of constraints.
Yes, and you can decide what that is later. So a video game example, because, this is all motivated by the reality that I come from, right?
Yeah.
So we have these game engines, and an object in a game world, we don't use the word object because that got commandeered by object-oriented,
really
right?
Commandeered and slaughtered.
Yeah. So we call them entities, right?
Thing. Right,
even though
go.
somebody else, right? So my coffee cup is an entity, right? And so entities have data associated with them and so forth. And you might have different kinds of entities, like a person. You probably want a lot of different things to happen for a person than a soccer ball, right? Those are very different. And so, we tend to make those different types of entities, and somehow they end up having different behavior and so forth. But, the way people have different ways of representing this, of course, but the way that I tend to do it is like a very, very shallow inheritance thing where there's there's a base that's like entity and it's got all the things that are common to everybody. And then like one level subclassing maybe, right? Other people do that a different way, but I think the way I do it is probably among the most common, right?
And are you inheriting the interface or implementation or both?
Well, it's not really about interface and implementation is the thing. It's just like, look, there's the data and do what you want with it. Like there's not getters and setters and whatever, right? Usually.
Right. Okay.
I don't find those to actually solve any problems.
Amen.
So usually an entity will have an ID, like it's got some handle that you use to look it up. It's probably an integer or functionally an integer. Maybe it's a couple fields packed into a thing, right? And so because there's a coordination problem, you have a lot of things moving around in a game and like something gets destroyed, right? You blow it up or it gets paged out to another area of the world that you're not simulating anymore or something. And you have to work within a limited amount of memory. So you have to destroy these things, but the nature of a game is all these things want to coordinate with each other all the time, right? And so if you just naively delete something, then some other entity that's trying to follow that thing is now following uninitialized memory or something, right? And so what do you do? Well, often you'll refer to things with a handle. Yeah. Modern C++ people, I'm putting air quotes as I say that because I think it's a silly phrase, but those people would say like you should use some weird kind of smart pointer for that. Oh, but that's not actually what you want to do because you want to have like very clear and authoritative control over what is the memory for this thing, when is it live, when is it not live, exactly what happens at exactly that moment, right? Which smart pointers are more about like kind of hiding things and magically stuff happens later when I don't exactly know, right? It's the wrong thing. So anyway, so you have some integer ID that you use and you say, hey, give me the pointer to the entity that corresponds to this ID that I like, say I'm following this entity. So I get back that pointer, or it says, oh, it doesn't exist. And because there's a specific time at which this happens, you're going to handle the non-existing case because it's obvious, right?
Right.
And then it's like, okay, I'm going to start looking at all this data, which might be quite a lot of data. I might need to use it a lot. So I take the pointer for a while and do stuff with it. Now, we have a safety problem, right? Because like, okay.
When are you done with this memory?
Yeah.
Right.
And so in games, the way that's traditionally handled is there's a very natural barrier, which is the end of the frame, right? So we do a bunch of stuff over and over 60 times per second or 200 times per second, whatever, right? And at the end of that frame, we pretty much know that
it's all garbage now.
Well, we're not really hanging on to anything, right?
Yeah, exactly.
And so it's a very clean cut, let's say, right? So, well, it's a very reasonable thing to say it's fine to do that stuff as long as you don't hold an entity pointer across a frame boundary.
Interesting.
Right?
Yeah.
Now, that's not a very generalizable rule because what's an entity pointer versus a pointer to something else? Your compiler doesn't know that, right? But you know that.
Right.
And so when the new guy shows up or the summer intern shows up and writes some code where he puts that entity pointer into a data structure that
actually is surviving across
like
a frame.
Some hash table that's sitting around, right? That's going to be a problem, right? And that's a very practical, real kind of problem. Yeah. It's not an academic made up problem.
Yeah. So how do you
actually can solve that? Your metaprogram can say like, well, you put an entity pointer in this data structure and that data structure is not in this whitelist that I have over here. And so error. You don't compile, right?
Right.
And so you can start solving the very specific problems that you have without introducing general friction. Now, is that better than the REST approach? I don't know. I think it will be, but I certainly offer you no proof of that statement.
I think it's interesting because it's grimier a little bit in that it is like less academically pleasing.
Yes.
Because it's like, oh, but I should have a type system that should, it should be the type system that should enforce that, and as opposed to this kind of programmed logic. Because effectively you have a dynamically programmable type system.
Yeah, well, it's not really. I mean, I don't think of this checking as being part of the type system, right?
Because fair.
So the type system is like, it's like what you would get if you went back to like somewhere between C and C++ and then made all the decisions the right way instead of the wrong way.
Yeah,
about like what automatically casts to what.
Yeah. And you're allowing it yourself to like, you're saying, I'm going to have programmable logic about what can be casted to what. Not in a smart pointer, but presumably at compile time, right?
Well, not even really.
Does your logic execute does that intern that made the mistake, do they know that at compile time?
Oh, yeah.
Interesting.
Yeah.
Yeah. That's cool. I like it.
Yeah, but it's not through the type system.
Sure,
So,
right. Yeah,
exactly.
yeah,
It's
yeah,
like
right.
The type system is made available to your arbitrary code, which then does this thing. But anyway, so
That's very practical, I think. I think it's neat.
yeah.
Are
But-
you going to, is the intent to get this broadly out there after?
Well, closed beta begins by the end of 2019.
Okay.
Which is pretty
that's
soon.
very
That's very
exciting.
soon.
That's coming right up.
I don't know when this will air, so maybe
Yeah.
it will already have happened.
So it would be open source? Will be
Not initially.
No, sure. Okay,
you know,
but
I think in the long term, if you want people to use a programming language, they have to be
so
able to have source.
so the one thing it does remind me of a little bit is D, not mechanically from D, not from in terms of what D actually did.
I mean, D makes a lot of really decisions that are different. You know,
No, but I think that the meta decision that Walter Bright made was to have that be kind of the last proprietary compiler. And I think if D had been opened 5 or 6 years earlier, it
might have taken off.
I think it would have had a broader relevance. Again, not that I hate the idea that we all need to pick winners. I think it's ridiculous. I think that it's if it's a solution for someone's problem, it's a good, that's great. But I think it sounds interesting.
Yeah, okay, so going back to Rust for a second, one of the things that I like about it, like I said, is like, okay, we're going to approach this problem of memory safety through compile time management as opposed to runtime management.
That's right.
Right?
I mean, but it does force you to really accept some limitations.
Yes, that's a non-trivial statement to make that has a lot of implications, right? But at least it's starting to rethink some stuff. And so going back to...
But I think you have a good point, because I think that one of the kind of system that Rust struggles with is where you've got a lot of interconnections and interdependencies. So to the point where it's advised, and I think rightly so, that like you want to get away from these complicated object graphs where everyone's got a kind of pointer to everybody else, because Rust, those are going to be multiply owned data structures, and Rust is going to bridle at that. You can get it to work, but it's ugly.
Yeah. Well, and then a lot of what people do sometimes, it seems like they don't realize that they're skirting around the system, but they really are. So for example, I mentioned I have a rant on YouTube.
Yes,
it's not an angry rant, but it's like I saw. So
this is what I see about my rant too. Thank you for saying that. It's like it's a rant with like a glint in the eye.
It's more of a rant in the sense of unprepared, right? I spoke for an hour unprepared, but so basically another company in the games industry was experimenting using Rust. There are a few people doing this, right? And we'll see how it goes, but for now it's the early stages of an experiment. And one of the engineers from one of these companies did a presentation at RustCon, I guess, is that what it's called? Where she said, hey, here's what I like about Rust, because it led me toward this design of a way of doing this entity system.
Yes.
So that entity problem that I was talking about before, right?
And this was a talk at RustConf 2018, I think.
Something like that.
Yeah.
Pretty recent.
Yeah, recent. Yeah. It was a good talk.
And so, what I said before about, what happens if one entity is following another one and one of them goes away and you have uninitialized memory, right?
Yeah.
Well, that's exactly the kind of memory safety problem that Rust is supposed to help you figure out is there, right? But this particular system, I don't want to go super much into the details, but the point of it, there's this thing called entity component system, which is a different structure of doing this. And mostly what that phrase means these days is sort of it's laid out in a data-oriented way. So if you're going to get the memory for a new entity, it's like maybe in some pre-allocated arena with all the things of the same size. So if you were to allocate and deallocate, you could like grab something out of that spot and put it back, and there's like no fragmentation or anything like that, right?
Right.
And so, but this entity component system that was being, the virtues of which were being extolled in this talk, was essentially a custom memory allocator, just where everything was the same size. So they were the same type, so that the type system wasn't getting angry, right? But like it still has, you still could have a use after free bug that the compiler wouldn't catch, because the compiler just doesn't know this is a memory allocator, right? And so I keep seeing things like that where I'm like, I'm not sure that the amount that's being paid is worth what is actually being gotten, right? However, I greatly respect the fact that Rust is going in this direction, and I wish a lot more people would, like where we kind of need to have some new ideas about how to program well, because we've been following the old ones for a while and we've kind of seen where they go, and it's not that great.
It's not that great. Yeah. So, and I think that this also, I think we may well see, and I should think we should see some bifurcation in languages around purpose and around where, because I do think that Rust struggles, because I've thought a lot about like, what does it mean to like rewrite the operating system in Rust? And there are a lot of things where it's like, it will be grisly and it will have limited utility and limited payoff because there are so many multiply owned data structures. When data structures have true multiple ownership, it means that in Rust, you're going to have to pull tricks to get that to work. But there are lots of data structures where you have multiple ownership, where you don't actually need to have multiple ownership. And if you rethink your problem and recast it in a way where you've got that ownership kind of going one direction and where things are singly owned, then Rust says, hey, if you can recast your problem this way, in return, I'm going to give you a high-performing artifact that is safe.
Yeah, and I think that's valuable. However, I think also, there's always people who are very overzealous about any particular idea, right? And I think the people who are overzealous say that that's 100% of it. Like, you always can make your program better by getting rid of the multiple ownership, and that's not true in my experience.
I think that's fair. Yeah, I think that's fair.
And like sometimes, like your problem is your problem, right? Like engineering means that you're confronting reality.
Yeah.
And reality is what it is, and you don't get to decide what it is. As an engineer, you're dealing with reality as best you can, right? So
if your problem has that tight interconnectedness, I think it's
going to a simpler example, right? That takes the Rust part out of the equation for any Rust enthusiasts who are listening, right? One thing people will say is like, oh, your program shouldn't have global state at all because global state invites bugs, in all the ways that we've been told. And okay, that's a true statement. Like, all things being equal, if you have global state that you don't need, it's probably bad. You should probably get rid of it. And I agree with that, right? But actually games have tons of global state.
Yeah.
Because like actually a lot of the problems that we need to solve, the actual problem is a global state manipulation problem, okay?
Right.
And so pretending that it's not, by saying like, look, I have a functional language and I'm going through 7 layers of things so that I can avert my eyes sufficiently from the fact that I'm actually just manipulating globals at the end of the day, right? That's just an obfuscation. It doesn't actually solve any problems. It certainly doesn't make you fast, right?
It's like global washing.
Yes. That's a good term. Yeah, I mean, even like, I don't know. We won't start talking about singletons and how they're totally not globals.
Right, exactly. But I think that it's a very good point that your problem is what your problem is.
Yes.
And the task should be to find something that is tightly tailored to that.
Yeah, and so when I get into arguments with people about this, I try not to because it's just hard because like I've seen problems that are multiple ownership problems fundamentally. They just are, right? And so you can't tell me to refactor that until it's like saying just refactor your program so it runs on the cell processor fast. What's your problem?
Right.
And it's like, well,
wait a minute. Yeah, no, that's a good. Well, no, and I really feel this way around doubly linked lists. Doubly linked lists are a multiply owned data structure, and I think that Rust advocates do themselves a disservice when they say you shouldn't need a doubly linked list. Yeah. It's like, hey, screw you. I need a doubly linked list for this problem. Or for this problem, my problem is what my problem is. Now, I think I would say that most people in the Rust community are much more balanced about this, of saying, hey, you can do that if you need to, but if you can possibly recast your problem, if you can let go of that particular way you've implemented it for a second, if you can recast your problem in this other way, you can get this great dividend. But I think there are problems that are not going to be able to be recasted that way. I mean, and that's just
But that's okay. I mean, we're figuring it out. Like, does anybody think that programming, assuming the human race exists, in 300 years or something, does programming 300 years from now look like programming today? I don't think it does.
Ooh, that's a great question.
And so, like, I don't know what it looks like. I have some ideas about what it looks like. So you were talking before about like, everybody can program kind of things.
Yeah.
Like President Obama, everybody should learn to code. Like, I think that's, on the one hand, I think people are right when they say that that's a computer skill. But on the other hand, that's different. We don't say like everybody should build a bridge that traffic drives across, right?
Right.
We also
don't say that everyone should write literature. I think everyone should be able to read and write. But
everybody could write their poetry in high school or whatever. Like, that's not bad. But we don't say that everybody deserves to have their novel read by the nation.
Right.
Right. And so those things, there's just some clarity there that we have not reached when it comes to software.
I think you're right. I think you're right.
And I think it's good for people to have technical skills to know how to program. I think, what does it look like when people who are not like bridge builders, when they program, I think it looks different from when bridge builders program. I think maybe, so in games, we have these systems that are visual programming kind of things like blueprints in Unreal or things like, it's like, connect boxes with some lines to do a thing that kind of looks like a circuit, but you get around like, infinite loop problems and flow control problems, and you kind of don't have pointers or anything, right? Very simple, still a limited model, but I think, the future for like non-low level programmers starts to look like that eventually. It doesn't, it doesn't
agree.
look like JavaScript, for example.
Right. I think that computational literacy actually is important as a universal attribute, but that doesn't mean that everyone is going to be at arbitrary depth. And it certainly doesn't mean, should everyone be writing Rust? No, probably not, actually.
Certainly not everybody, but should everybody who's building bridges be writing Rust? Well, Rust people would argue yes. And I would say, I would say I don't 100% agree, but we shouldn't be writing C++.
Amen.
Okay.
Yeah, there we go.
Yeah.
Well, and the 300 years thing is kind of interesting because I still believe that we are in a golden age of software still. And I think that we are laying down track that will be, especially as we take some of these big and important iterations. I do think Rust is an important iteration. I think that JAI, whatever it will be, whatever will be renamed, Diamond Dust, is potentially an important iteration. I think that we are going to take some of these big important iterations, and I do think that we're going to be building things that, the Romans laid down a lot in terms of civil engineering. And the Greeks laid down a lot in terms of philosophy and how things are constructed. I think we're laying down a lot in terms of how future software is constructed.
Maybe. I mean, yes and no, right? So one of the things that I can shill here, I have a different video on YouTube. It's a lecture I gave in Moscow this year in March called "Preventing the Collapse of Civilization."
Okay.
Where I do agree with the fact that we're producing a great deal of software, but I sort of note that these days we don't really expect it to kind of work that well. Like computer bugs have always been a thing, right? But like these days our expectations seem to be lower and lower. And
that's where I do take issue with that, in that I think our expectations should be higher and higher, in that we should be writing software for permanence.
Yes, and I agree with that. And the problem is we're not really. And and there's all sorts of weird stuff going on. So you mentioned, like NPM kind of things, right?
Yeah.
So my understanding of the way NPM works is when you build something.
Oh, you've had such a charmed life.
Yeah. No, I've stayed away from that stuff.
You really have stayed away.
I mean, so when you build stuff, the tradition is you just sort of pull down the newest version of any dependency that you have. And of course you have like 37,000 dependencies, right?
Yeah.
And so everything that I've learned from making video games, which are very complicated and have to work well, right, is that the way you ship software that works robustly is so all these obvious things, like of course you test it, right? But what does that mean? It means you test exactly the thing that you shipped. It means if you update some submodule, you don't do that without like fully testing it. And that's not like automated tests. That's like playing it for weeks and weeks, right?
Yeah, right.
But also it means you know what's in there and you know how it works, which means you probably don't have 37,000 dependencies. And it means that once things are established to work, you kind of harden it. You say like, this is the product. Like, we're not going to go have a summer intern swap out parts of this product when nobody's looking in 6 months.
Right.
Because like the thing that we have vetted
is done.
This is the thing, right? And that's very counter to like what the web people are doing these days. And I kind of,
it's interesting. Because, all right. So no, I see what you're saying, because one of my criticisms of games, such as it is, has been that it's a lot of software that's thrown out. But because there is this emphasis on completing the artifact and not constantly evolving it, there is a higher bar for the correctness.
We throw out a lot less than we used to. So back in the Doom Quake days, we would throw everything out every time because what we had to do was so different. Nowadays, that doesn't really happen anymore. But the thing that weirds me out, and the more and more, so the thing I've been doing for the past year or two is like looking around and saying like, wait, where are we with respect to all this software stuff? And like, what happened exactly.
Yeah.
So, for example, if you go back to the 1970s, invention of Unix or something like that, right? What is that? It's an operating system. What does operating system mean? Well, it's a thing that just like helps you run programs on this computer, right? That was relatively laborious to like start up programs and get them going, right?
Yeah.
And so now we have a system that helps us do this, right? So we're 50 years later. It's a long time.
Yep.
And we have operating systems still. And I don't seem to be able to consistently run software on them. Like, whether it's, Linux or Windows or something like that, distributing a program on Windows that I will know will work on someone else's Windows computer is really non-trivial. Like I don't care what the program even does. Like once you start getting into things like how it interfaces, but just like, do I know that it's going to start up correctly or it's going to pop up some missing DLL error box? Like it's hard to know that actually. And the only real way you can know that is by abandoning a lot of the stuff Microsoft is trying to get programmers to do and having very little in the way of dependencies and really like focusing down on that. But like nobody steps back and says like, but wait, why is it so hard to run a program? You know, on Linux. So Linux has a different aesthetic, right? People sort of expect that you don't distribute precompiled binaries there.
Right.
But like one of the reasons is just that it's so hard to do that and have it actually work for everybody, right? And not just like Linux people will say, oh, it works for me, haha, whatever. But like when you have to answer support calls, you really get a clear view of when things are not working, right? And you really see like, oh yeah, on this percentage of systems, on 8% of systems, this thing just doesn't run. That's a huge disaster, right? Because you'll get killed by support calls, right? But anyway, so this is I think you worked at Docker, right?
Yeah.
And so containers are one of my pet peeves because we've somehow
That's great.
We've somehow like if you go back to like the 70s or 80s, like you had a couple of computers, they were the same kind. You just copy the executable and run it.
Yeah.
Like I remember doing that in college, right? So and then somehow we've made this several layers harder by like, okay, so you're actually linked against dynamic libraries, which it seemed like a good idea at first, but now this other system has different dynamic libraries, right? And so it may not run even though they're named the same and you don't bring them with you. So like that's...
Well, I think containers are a reaction to that, right?
Well,
Containers are trying to get you back to that model you had.
Yes, and I have no problem with that as long as somebody says, wait, this is just covering up for a problem that we solved. And so maybe eventually we should go back and like collapse these layers and resolve the problem. But if you go on like Hacker News or something, right, where the 24-year-olds hang out, they think this is advanced software technology, that you have a container and that this provides a new layer that like gives you new capabilities. And I'm like, no, dude, I could copy a program over the network and run it in, the 70s just fine. We lost that capability. And actually one of the points that I put in this Russia talk was, it's even weirder than that, right? And especially in games, but broadly speaking. So if you have a Windows PC and a Linux PC and a Mac laptop and a PlayStation 4, those all have compatible CPUs in them, right? If you have a machine language program that you just magically teleport into the memory of those things, and if it doesn't go out to the operating system to do anything, it's just computing a result. It will run on all four of those things with no problems. Perfectly. Perfectly. And yet we have so we have this capability of perfect cross-platform compatibility, right?
Yes.
By virtue of the platforms being the same, but whatever.
Yeah.
And we have somehow subtracted that at the operating system level.
Yeah.
For what reason? Hopefully a good reason. No, it's just like the executable format's a little bit different and whatever, right?
Yeah.
Like reasons that aren't, like all these operating systems are kind of doing the same thing. They're just doing it in incompatible ways that don't really buy you anything, right? And then, okay, so the really horrible thing for the future is we are now in an area where these kind of infrastructural decisions are being made by companies who don't seem to have any incentive to cooperate anymore in a sense. So going back to the C programming language, pretty good idea back when it was made, I guess. A lot of people would think it wasn't particularly good.
No,
but
anyone who's going to complain about C is ordered to spend time in the languages that immediately predate it.
There are reasons why C was successful.
Absolutely.
Let's put it that way.
Yeah,
right?
I mean, C is way better than what comes before it.
Although I wish that they had done that they had actually type checked parameters in
nice.
KNRC. That would have been great.
That would be great. Yes, yes, yes.
The open paren close paren thing was not good.
It really wasn't. It was bad. Yeah.
That was my first C experience. Was like, why is this crashing?
It's like, oh, because a signature is optional? It's like, yeah, right.
Anyway, but back then it was like, look, we have this language. We can compile for multiple CPUs. The CPUs might be quite different, right?
Yeah.
We might have to make some allowances in the code. So we do some if-defs around small portions of the code where like, I don't know, if we're running on something that doesn't have a certain size integer or something, do this, otherwise do this, right? Whatever.
Right.
We're all very familiar with that.
Right.
That is a good model, right? That got us a long way. Eventually that got replaced with this interpreter languages model, which I could rant for hours about why that's weird and not what we think it is, but I feel like we're going kind of long. Like, I don't know how long this is supposed to be. But anyway, so the problem is now, okay, so we've had this new hardware introduced, like GPUs, right? GPUs are very fast at doing the thing that they do. And then your job to render graphics is to talk to the GPU or to mine Bitcoin or whatever you're trying to do, right? And so how do you communicate across that barrier? Going way back, it was just the data communications. You would like upload your image data for your texture maps to the GPU, and then you would just send commands through a command buffer where the commands were just like some bytecode that says like draw this triangle or something. It was pretty primitive back then, right? It's gotten more and more complex where now, it certainly rivals a CPU or exceeds a CPU in complexity. And so we have programming languages for that, right? Now so we call these like shaders, right? Which that name just means, it's how you would compute the light on a surface originally, but it doesn't make sense because now we have like compute shaders, which just means it's the program that runs on the GPU that runs an arbitrary function, right? Whatever. Okay, but all of these languages are being done by either GPU vendors or people who are trying to standardize their graphics API or people who are doing both, right? So operating system people, GPU people, okay? So we have the opposite of C now. Okay, what we have is I can have a system with an Intel CPU, an NVIDIA GPU, right? Hard drive, whatever. If it's running Linux, I have to use one shading language because I'm using, let's say, OpenGL or Vulkan, right, to do the rendering. If I'm on Windows, I'm using DirectX to do the rendering. So I have to use a different programming language.
Right.
I can't compile the same language to a different target. It is a different programming language that, by the way, in much the way operating systems are different for arbitrary reasons, but they're all doing the same thing. All these shading languages are different for arbitrary reasons.
Yeah.
Yeah. And so now we do all this like transpiling from one shading language to another, like in the background. And if it's hard to have like a serious program when you're doing it, you can't program in the same way anymore, right? Right. And like nobody,
that's getting further away from the ultimate from the hardware.
There's no adult supervision. Like nobody's looking around and saying like, wait, what? Like these programs are actually simpler. Like, so C programs were like manipulating data structures and going into the operating system and all that. Like shader programs are actually simpler. They're just mostly doing math.
Computation,
and outputting numbers.
Right.
That's a strict subset of what we used to do. I mean, you start doing weird data structure stuff these days because GPUs are more powerful. But like when you do that, it's in a more streamlined way that is just simpler. It doesn't require the kind of iron behind it because you're programming to the GPU as opposed to expecting the GPU to come to you, right?
Right.
So nobody's looking around and saying like, what?
Right.
Why is this happening? And certainly nobody is trying to prevent it from happening, right? Like imagine if like you just like a Sun workstation used a different programming language from an Apollo workstation, which used a different programming language from SGI, right? Like what would have happened? I don't know, but it would have been a mess.
Yeah, but I think that also leads to that tension is what leads to these revolutions, right? It's like we're right. I mean, because what came before C was a mess. It was people doing exactly that, where the different language that I have on these different machines was the assembler. And the assemblers were different for all these machines, and C was what came in and so I mean
we could say like before Fortran or something. That was the situation, right? Or,
Yeah,
or
right.
did enough people object to Fortran that they just would rather be an assembler? Or?
Well, I think for systems programmers, Fortran was not a real option.
Okay.
Right. And so operating systems themselves had to be written in the assembler of the machine.
Right.
And that is what, and C, that was kind of C's gift, is that you can now write a portable system software. And I think that I think that part of why, I think there is still so much to be had in new computer programming languages is because we have not yet, I think you see this with Rust and systems programming, and maybe with the future diamond dust in games programming, where it's like there actually is innovation to be had.
There's a lot. So I'll give the short version of my interpreted languages spiel, because we're roughly contemporaneous. You'll know where I'm coming from on this, right? So in the 90s, we were still under this impression that like Moore's law is infinite. Right?
Yes.
And
this is what I call, this is the true golden age of Moore's law.
Well, okay. And there's this history of programming languages that had held up to that point, which was back in the olden days, we programmed in machine language.
Yeah.
And that was just very laborious. So we made assembly language, which was a higher level text representation.
Right.
Compiles down to people these days don't think there's much of a difference between those two things, but try it. It's really different.
Yeah, it is. Yeah, right.
Okay, so then assembly language is still very mired in details. And so then we started having higher level things like Fortran or C, right? And then maybe depending on what political party you belong to, maybe Lisp was the more powerful next step, or maybe it was like Modula or C++, whatever. Right.
Mesa.
But the point is, the point is there was this way that we had been proceeding that was obviously true, which is that the higher level your language, where I'm again putting that in air quotes because we still don't exactly know what that means.
Right.
But the higher level your language, the more powerful the programmer is, right? The more abstracted they are from the details of what's happening.
Yes.
And then the more productive they could be.
Yes.
Right? And so then the problem is we made a conflation in the 90s.
Yeah.
Which is higher level, which is something about power and expressibility, and far from the CPU, because those things had been correlated. And so we just started making all these languages that were far from the CPU and that seemed higher level, but in ways that are actually a little bit trivial. Like, okay, so I could say string plus an integer, and like it'll convert that to a string and like and that for the first 10 minutes when you sit down doing that seems really cool, right?
Yes.
But like, does that help you solve hard problems?
Yeah.
Or does it get you started faster on easy problems? It's the latter one. And it actually causes hard problems later.
Amen.
Because you have no type system, right? Does this variable exist? No, let's make a global variable that's the empty string because you typoed somewhere.
And
right?
you are a math concentrator, not a computer science concentrator, so you might not have gone through this kind of youthful experimentation with operator overloading, which is what Jonathon is. And it's where because the first time you discover operator overloading, it just seems like awesome. And then at some point, you need to realize that like, actually, this has not made it easier to solve hard problems.
Yeah, but I would even go more general than that. That like we had all these kind of very managed languages at that time, right? So like Tickle, which is one.
There you go.
That's in the extreme where like everything is a string all the time. And Tickle programs never would work 2 months later.
By the way, Tickle is alive. And one of the things that Jess and I have been doing is we've been doing a lot of low-level stuff in terms of the EDA and FPGAs and so on, where Tickle is alive and well and thriving.
People use that.
Oh my God.
Okay.
No, we get like software that generates Tickle for for these FPGA synthesis. It's insane. I've never seen more Tickle in my life than I have.
Doesn't that sound good to me? But so Perl from that era, Python, right? Python's still in heavy use today, unlike those. Well, I guess you're telling me Tickle's in heavy use, but like Python is still used. A later variant of Python is used by many programmers, right? So the thing is, like, okay, how high level is Python really? It's probably higher level than C. I would agree with that. Is it as high level as people think it is? Is it high enough level to pay what we are paying to run all these Python programs? I'm not sure. Because there's sort of multiple things that happened at once. One is this programming language is like, say it's a lot slower because it's running interpreted and all this all these things. But also there was like a different kind of community that started happening around that time where source code was shared much more readily and all of this.
Yeah.
And so part of what's appealing about those languages is just how fast you can get started because there's just a lot of code, right?
Yeah.
Similarly with JavaScript and all this stuff. And so
batteries included.
like JavaScript is so weird. Like that was not ever supposed to be a real programming language. And somehow
no, it will
like it was supposed to just be like, this is a way you do some simple if statements on a web page.
Right.
Like that. Yeah.
Well, in JavaScript's, I mean, its birth is in its own kind of metastasis. It was not supposed to be what it is. In fact, Brendan Eich never wrote a book on it. And this is one of the, anyway, yeah.
Yeah. But the point I was trying to get at is just, there's two parallel stories, really. There's that one story of like, here's the sequence of programming languages. And as the programming languages get bigger and slower and farther from the CPU, that's okay, because CPUs are going to get faster forever, and we become much more productive, okay? So are we more productive in Python? I'm not sure, because like, you can keep seeing all these examples, like Dropbox published this thing in early 2019 about like, hey, here's the story of us migrating from Python 2 to Python 3, our 1.2 million line program for our desktop client. And I'm like, wait, what?
I have so many questions. My hand is up in the back.
And I don't mean to single out Dropbox, because like, if you just start looking around at this stuff, you see it everywhere. You see so much code for all these things. And I'm like, wait, if this language is so high level, why do you have so much code to do such a small thing?
Yeah, right.
And so what you see when you look around, I claim, and it's, I haven't done a double-blind, triple reproduced study on this, but like, it looks to me like the productivity levels of Silicon Valley engineers are historically low, actually, in terms of what they produce.
Yeah.
Not necessarily in terms of lines of code. The lines of code is very large, but in terms of actual functionality produced per engineer, it's low. And so something went wrong.
That's because everyone always has to be hustling. I know. This is like, no, this is the hustling.
I know.
And that's fine, right?
This is the long shadow of Uber and always be hustling, where everyone feels like, I need to be productive today. And I need to be, it is better for me to regurgitate code than it is for me to reflect on a hard problem. I do think that is right now very deeply entrenched.
But at some point when you have like an order of magnitude more code than you should, right? Which is not the order of magnitude that computer scientists are supposed to be thinking about, order of magnitude of like speed or something.
Right.
Like order of magnitude of code is a weird concept, but like, doesn't that have to kill your company eventually? Right. Yeah. On a long enough time horizon. Maybe it's just longer than people are thinking. But so regardless of that, regardless of the business case for that, which is something that people will argue with all day, right? There are supposed to be people who are the custodians of the field, right? We are the people who really care about computers. We're trying to make sure that computers are good and like that the way we program is good and all this stuff, right? And I don't feel like enough of those people are looking around and saying, wait, we're in crazy town right now. Because this didn't, like, the claimed benefits of all these things did not happen. And why not? I mean, maybe they happened 10% or something. But like and then there's a whole other thing, right? Which is, if you go back to something like C, like I said, my initial user experience of programming in C was horrible, because initially it was KNRC. And maybe it was NCC, because this was like 89, 90. I'm not sure. But I was learning from the KNRC book, so you still didn't type procedure prototypes or whatever. But the point being, there were all sorts of dumb crashes. And then even later, all sorts of dumb things. So the thing that's very easy to do in C, have an uninitialized variable. I put it on the stack, I didn't set it, and I used it later. Right. Okay.
It's like
many programmer millennia were wasted debugging that kind of thing. I'm sure. Like if you were to compute the amount of time
that's an entirely preventable problem.
Yes, it's trivial. Actually, I mean,
it's like the computer knew what it was doing when it did it.
Solving 100% of that is not necessarily easy. But like, look, just have a debug build where for local variables you have an additional Boolean or something, and just add some instrumentation code that checks if you use that. And set it, so maybe you don't know if it's assigned.
But this is what you do have to like about Rust. I do like about Rust is that it doesn't actually defer that to a linter. It forces that cognitive load right back on the programmer.
Well, so the thing that I like about the mood today is we're starting to realize that these things are problems. Even if you go back to like Clang or something, I think they have that kind of thing in there now, right? Yeah. But the point is, we went many decades without that.
Yeah.
Where you're just like, maybe that's why I don't have that much hair anymore, is because I was pulling my hair out, in the Apollo lab trying to figure out why my C program was crashing, right?
Right.
A lot of these languages that were designed later, including probably stuff like Java, which I also don't have that much experience with, but I assume you do, having a son history.
No. My experience, no. I was always a Java malcontent and conscientious objector.
Anyway, though, a lot of this thing that happened was a reaction to stuff like C. Like, look how terrible it is to program in these languages, right?
Right.
But the vast, let's say 95% of the unpleasantness was actually completely unnecessary. If anybody who was making those compilers had cared about the programmer really.
And I think you're right. And I think that one of the reasons that I was not a Java programmer, one of the problems I had with Java was its assertion that the programmer was too stupid to do to have any kind of memory safety and to do memory management. Memory management's impossible, so we are going to completely take it out of the programmer's hands.
Yeah.
And what people ended up, who are building sophisticated systems in Java, end up spending all their time on memory management, namely trying to outsmart the garbage collector or feed the garbage collector. It's like, do you realize that the problem you're solving is just as hard as fucking malloc and free?
Well, it's actually worse because this happens in games all the time too, because a lot of people use C# or whatever. There's like game engines like Unity that uses C# as its primary language. And I get into these arguments with people like, look, you shouldn't use... And they're like, no, garbage collection is fine. Just do this and that and that. And you're telling me about memory management,
Yeah, exactly.
Right? But after you've done all those things, you still can't really prevent the garbage collector from kicking in. You never really can, especially if you use a library somewhere that you don't control.
Absolutely.
Right? And so you've got now you've got a performance problem, and you're doing most or more actually of the same kind of engineering. And people don't, like, again, there's not the adult supervision to say, okay, wait, it was an interesting idea to say that everything should be garbage collected and nobody should manage memory, but it hasn't worked out. Like, somebody has to do the accounting of, like, what did we expect back when we started this idea that the benefit would be? What percentage of that benefit do we have now? Oh, it's low? Maybe that wasn't that good of an idea. We don't have anyone standing around doing that.
So I do think people are doing that. It's just that they're doing it kind of in clusters and clumps. And I do think that a lot of the Rust enthusiasm is people saying, actually agreeing with that and welcoming a different kind of approach.
Yeah. So the other, I don't know whether to go off on this tangent, but so the garbage collection thing, of course, people will argue about garbage collection infinitely. But one of the reasons why I claim it's really turning out not to have been a good idea is in part this thing about memory being so slow relative to CPU cycles now. And so you, of course, the only real way you can ensure that that's good is by knowing where things are in memory, right? Yeah. People will say like, oh, our generational collector compacts things together sometimes stochastically. And it's like, actually, no, you could do much better as an actual programmer.
Yeah.
So that matters a lot, but also our demands matter a lot. Like I said, like games run at 240 hertz. Like, how much of a GC pause can you afford to take when your frame is 4 milliseconds?
Right. It's not that long. And a memory access is going to be 100 nanoseconds. It's like, this adds up really, really quickly.
Yeah. And so I'm that's one reason why I like the fact that Rust went this other direction.
Yeah.
It's like, okay, yeah, good. Let's start doing that. Right. Now, the thing that I'm concerned about there is, so I mentioned this data-oriented design thing before. And one of the tenets of that is that the way that you do things fast is by operating on large groups of things. You know, that's just what CPUs are good at. Like, just figure out what you're going to do it on this set of stuff, move on to the next set of stuff, right? And so conceptualizing things as individual actually will make your code slow, even if you didn't like spend instructions, right? You're missing like the opportunity cost of having had this bundled together with a lot of things. So for example, you know, some languages are predicated around memory management with like automated reference counting. That's one of the big things, like Swift or whatever. Right. Or the C++ people are all about like RAII, which stands for resource allocation is initialization.
Yeah.
Which is partially about memory, but also partially about like object state, whatever. I'm not going to get into an argument about that, but I believe that has very clearly not worked out. Again, maybe sounded like an interesting idea for the first year, really had a lot of problems, right? But when you conceptualize things as individual like that, you're probably not going to have arrays of them. You're probably certainly not going to have different arrays with like cross-cutting things that those guys care about, which is what you actually need to do on a CPU. So in that kind of world, like automated reference counting is not that useful unless you wrote everything behind the reference count anyway, right?
Yeah.
Which is what people are trying not to do. And so what the thing that I try to explain to programmers is like, look, this memory speed thing isn't going to change anytime soon.
Yes. So the other thing it tacks into exactly what you're saying is like Moore's Law, we're done. We're
not done, but
we're done-ish. No,
I mean, well, people don't remember back in my first game company, we bought new computers every 6 months,
right?
Because our productivity would be way, 48660, 48690 or whatever, maybe 66 to 90 or 50. I think I had a 50 at one point. I don't remember what the numbers were, but the point is, in 6 months, you could get that much faster.
Yeah.
That's not a thing to do.
No,
and it changes everything.
It changes everything. And I think that I think we're going to get back to an era where people are looking at what the actual artifact is that's generated, how that actually runs on the metal, and how we can have better abstractions that allow us to better express that in terms of the running artifact. And so, I don't know. I feel optimistic. I feel that we've gone through a bunch of experiments, and that you now have, I think, because you were saying that, like, where's the adult supervision? I think that we have enough miles on the tires on some of these things that you are now seeing groups of people who are like, no, we've done it that way for a long time. And now actually we've seen all the problems with this.
I hope you're right. The thing is, I am relatively vocal about these things lately. And whenever I say stuff, especially somewhere like Twitter or whatever, but even in other venues, I get a mixture of a lot of people telling me I'm wrong, right? About
but those
whatever,
are
right?
I mean, like Twitter is like the worst place for that.
But also then a lot of people saying, oh, none of that really matters because like, my slow React application is the future or whatever. And they might actually be right to some
but
degree.
Here's my counter on that, and then maybe this is just like fundamentally elitist, but I just, this is in my marrow, is that the number of people that are writing that software that is at the actual brainstem is a smaller number than the people that will write all software. And the people that we're talking about who are writing the core of game engines, who are writing system software, it's a smaller number of programmers.
Well, okay.
So it's actually okay to shift that cognitive load to them.
There's a real problem though, which is the following: that the people who want to ship the slow React application a little bit do have a point in that. Like, what's their alternative? Okay, make a native application that they cross-compile for all these different platforms. We have made that very, very difficult.
Yes,
we have made it an insane cluster F to do all those things for essentially no reason.
Yeah,
there's just a lot of implementation details that have historically accrued, and to tell somebody who can just sort of write their high-level scripted thing, like, oh, you should do this native. It's like it's a big change for them in terms of,
but I think it's okay.
Things that aren't that important.
So then right, exactly.
So we need to start fixing that stuff.
Yeah.
And nobody seems very concerned about that. Right.
Yeah. I just feel it's got to start at the kind of the bottom of the stack in terms of like
possibly, right? So, I mean, there's all the
bridge builders, the bridges, as you pointed out.
Well, so I think that's a little bit happening a little bit wrong to some degree, right? So there's the rewrite it in Rust people, which
right.
I think that's a thing that makes sense, especially when it's very well defined what the thing is.
That's right.
Here's a utility. Right. We know exactly what it is.
We know what the abstraction is.
We're not going to go through some prototyping phase where we're figuring it. We just know we want it to be more secure.
We want it to be safe, secure, and high performing.
I think that makes...
And we know what it is.
Yes, that makes a lot of sense. The problem is the things that we're rewriting in Rust is not the right thing.
Yeah.
Okay. Like, so Unix is from 1970, right? And it grew, it changed a lot, but like, we're still doing 1970 stuff 50 years later. We like should have a better idea. And some of the better ideas may be things that we discounted. So like microkernel was a thing for a while.
Yeah.
And then it sort of lost this performance argument. Like microkernels are going to be slower, right?
Yeah.
Well, I mean, after all this Spectre and Meltdown stuff, the point that I always make is like, look, there's 173 more of these that like people just haven't found yet.
That's right.
I think now that we're in this age where cores are cheap, you're just going to have the model be your operating system gets a core and it just lives there.
Yeah, I think you're right.
And that's the secure thing.
Yeah.
And why not? Because you're not able to use that core anyway, because we don't know how to make parallel software well enough anyway. Or
actually, to your point, the problems are just not parallel enough. We just don't have enough problems that are parallel enough. We've got a lot of problems.
That's sort of what I mean by that. And so then, has anyone done that performance comparison? Like, is your microkernel really slower if your non-microkernel always lives on a different CPU? I don't know. Right. I don't know what that looks like.
Yeah.
But I'm just very concerned. Like, I'm writing a compiler, right? And
what are you running the compiler in?
Well, it's in C++, unfortunately.
I kind of figured it had to be.
But so our compilation model is different, right? So the compilation model used by C and by many other languages is that you compile your program in little pieces that are .o files.
Yeah.
And that's important for many reasons. First of all, so that you can interoperate with other languages and stuff, and you can link those .o files together. It also lets you do incremental compilation, right? It also lets you do parallel compilation, right? Because you could do all these things, right? However, it lets you do a bad job at all those things, and some of those things are not necessary. So, like the game that we have right now that we're working on is it's about 100,000 lines. So not giant, not tiny.
Okay.
With our compiler that's running mostly on a single core, with beyond C++ level features, what I consider to be better. C++ people might argue, but whatever. We compile that whole game in about, right now it's 0.9 seconds because we got
900 milliseconds.
Yeah, on one core. We compile output the executable, which includes spending 100 milliseconds on a link step because we output like one object file and then use the linker to turn it into an executable.
There's a Turbo Pascal manual to your right down there. I think it's glowing hot to the touch.
Yeah.
Remember Turbo Pascal?
I had that in high school, and we never wrote big things on it, but
it was such
it was like running on Apple IIs or something.
Yeah.
And here's So among the many rants that
Anders
I have,
Heilsberg, wherever he is right now, just suddenly feels happy. He doesn't know why. He's feeling a warm feeling.
It's insane. So one of the many things that I try to get people to realize is, look, it's insane how long compilers take right now. Like, if they're optimizing, you kind of have an excuse because you're doing like combinatoric things, right? But like, just to compile a program, like, look at like how big is that program as text, and how many operations per second can your CPU do, and so how long should it take? And why do we take orders of magnitude longer? And why does that time keep going up over time? Now, again, some languages like Rust have more of an excuse.
Yeah.
Because, all this correctness checking actually is combinatoric also. Yeah. Whether or not you should pay that every time you compile is something I disagree. But it's got a reason, right?
Yeah.
But again, like for most programming languages, we're compiling these things on insane supercomputers. Like these things, my phone is faster than the fastest computer in the world in college that used to do like, nuclear simulation stuff, right? And one of my peeves is programmers today don't understand this, right? Yeah. They open an application on Windows and it takes 3 seconds to open, and like they think that that's fine. And it like doesn't put anything on the screen after those 3 seconds.
Right.
And you're like, do you have any idea how much your computer can do in 3 seconds on even one core, right? Yeah. And so we're in this world where all these design decisions are made the wrong way. So I'm trying to simplify this stuff, right? Yeah. So like you run the compiler, you certainly have the option of just getting an executable out the other end if you don't have any dependencies in other programming languages, right? And it's real fast to do that. Trying to get that to work with different operating systems is really annoying. There's just a lot of like friction in the way. Why? What's an executable? It's just a well-defined file format where some things go in certain slots, right? It's just data. It's like writing an executable file is not that different from writing a zip file or writing a JSON file. Yep. But it's become this magic, scary thing that nobody is willing to do. And especially that we can't, I don't know. I guess some people have made inroads on this. Like, doesn't the Go compiler, can't that cross-compile and generate executables?
It's actually really nice.
Yeah.
The other thing I like about Go is that you can create static binaries like super easily.
Yes. And so we're going that same direction too. I think that's something Go got right that is like underappreciated.
Yeah,
right?
and that's what Rust does too. Right? Rust generates the binaries that have. Yeah, no, I think that is. I think dynamic linking may be another one of those like garbage collection kinds of things.
Well, dynamic linking, but even static linking, right? So you've got this thing at the back end of how you're assembling your program, which today, like, what does it mean to have a well-structured program? Like, it's namespaced interestingly, right? It's got, I don't know, we've got overloading, we've got whatever, right? And you go through the link step and kind of like the first person who uses a name gets it like invisibly or whatever. Like, what? It's not a good thing to have in the back end of your infrastructure, right? And that's just there. Like, there's problems that I have. So, we have hygienic macros, right? And so in principle, if you're in the debugger, you can step into your macro, right? And you see, okay, good, right? You would like that, right? Problem, how do you really put that in the existing debug format? There might be a way to do it in Dwarf. Actually, because Dwarf's so insane. But the problem is, if I set a breakpoint in that macro, right? Like, I don't know where I came from now because it's on like the stack.
Yeah, right.
It's in the stack frame of the outer function, but I've identified that macro expansion. It's maybe a hard problem to explain, but the point is, I can identify this. I can identify it as being in the macro or as in the function that called the macro, but kind of not both.
Right. Right.
I don't know Dwarf well enough to know if there's a way to do that. But these things are just, they're very complicated and they're very old. And if you were to design things from scratch today, they wouldn't look like what we have. And yet there aren't very many people willing to change the things that we have.
Right.
And again, back to the point.
Yeah.
The point that I brought up earlier about the point of an operating system is to help you run programs, right? If you install Linux today, it's insane. I have no other word than insane. Well, also Windows, right? It's insane. Like, my Windows machine wants to reboot itself every week, right? To install updates.
Yeah.
What are the updates? Well, they're mostly to software that I wish wasn't on my machine anyway, right?
Candy Crush. I can't get rid of Candy Crush on a Windows machine for like the life of me. It's like this demon that keeps coming back. I had to write a script to be a scheduled job on Windows to get rid of Candy Crush because it would come back. Like, it just runs every so often.
But like we've ended up in this world where like that's the minimal thing that you need on your computer to run programs.
Candy Crush is load bearing.
Yeah, no, it seems load bearing because it keeps coming back. It's like absolutely insane.
Yeah,
but like how do you? And meanwhile, okay, so we have this Windows that, by the way, has like probably 3 nines of reliability built in now because it wants to nobody even knows what 9s are anymore because we've given up on that idea of things being that reliable, except maybe in corners of enterprise software. And at the end of the day, I still can't like render something full screen in Windows without other windows like running to the other monitor or like flickering back and forth, and like things are still super broken, or like Windows handling of high resolution displays is still super broken, and all this complexity hasn't helped us solve the actual problems that we have.
It hasn't. So here's my hopeful note for the future is that I think that the abstractions, I mean, you look at Unix, a very persistent abstraction, and I do think that there are other abstractions. I think that Rust is a very important development. I think that there are other very important. The SQL is a very important abstraction. We develop these very important abstractions, and the history behind each of those abstractions almost invariably is someone who has started to deeply question the complexity and takes a katana to it and slices through the complexity and delivers an underlying simplicity. So I think it's like, and then the nature of software is such that that idea, it takes one person or a small group of people to have the guts and the stamina and the resilience to do that. And then when they do that, it's leverageable by a much broader cross-section of people.
Yeah. Can I, I'm going to throw out a stone that'll get people mad at me, right? But so in terms of all this complexity that needs to be collapsed, right? I think everything has its time. The thing, so the
God,
Unix.
What's next? What are you going after?
Well, like the Unix philosophy, for example, which has been inherited by Windows to some degree, even though it's a different operating system, right? The Unix philosophy of you have all these small programs that you put together in tool-like ways, I think is wrong. It's wrong for today. Yeah. And it was also picked up by Plan 9 as well, right? Yeah. And so
And
So-
microservices. Microservices are an expression of the Unix philosophy.
Yeah.
So the Unix philosophy, I've got a complicated relationship with Unix philosophy.
Yeah.
Jess, I imagine you do too, where it's like, I love it. I love it when I love a pipeline. I love it when I want to do something that is ad hoc, that is not designed to be permanent. Because it allows, and you were getting this earlier about Rust for video games and why maybe it's not a fit in terms of that ability to prototype quickly. Unix philosophy, great for ad hoc prototyping.
Yeah,
Sort of.
one-liners. Bash one-liners.
Bash one-liners.
As long as what you're doing like is expressible as grep or something, you're
Yeah,
fine,
yeah,
right?
Yeah. But then doing that is great. Just don't make that load bearing.
Right. Well, so as somebody who likes Rust, right, you probably agree with me about certain things. Like, look, if you're going to write a substantial program,
Yes.
right, that needs to work
Yes.
for a long time, and it's doing sophisticated things, as we often want to do today.
Yeah.
You want your data to be well-defined
Yeah.
and structured. You want to understand when you're dereferencing data that it's the right type,
Yeah.
right?
Yep. Yeah, exactly.
You want to be able to move data around quickly. You want to be able to, so all these things, right? That's what it looks like when you have a strongly typed programming language that calls out to libraries or whatever, I don't know, crates in Rust or whatever people call things these days, to do jobs. So that is the thing that we have discovered about how to put together a thing that does technical work at a large scale that does a complicated job, right? So all this Unix stuff is like, it's the sort of the same thing, except instead of libraries or crates, you just have programs. And then you have like your other program that calls out to the other programs and pipes them around, which is as far from strongly typed as you can get. It's like just data coming in a stream on a pipe, right?
Yep.
Other things about Unix that seemed cool, well, and the last point there is just to say, so we've got two levels of redundancy that are doing the same thing. Why? Like, get rid of that, right?
Yeah.
Do the one that works. And then if you want a looser version of that, maybe you can have a version of a language that just doesn't type check and use that for your crappy spell.
Well, no, I think we already have that. That's awk. I mean, this is what I love about, like, go use awk if you need awk.
Yeah,
But like,
something like that. But
I love awk. I love awk. I'm not gonna write 100 lines in awk.
Oh
Even.
God, who would do that?
Right, exactly. It's just like there's a bit of a right tool to the job.
Like I was more of a Perl guy, so I could see the point of something like Perl. Like put all the mess in Perl, and then it just lives there.
God.
Right?
But Perl became a super fun site. It became it's like we dumped so much crap into Perl that it became uninhabitable.
It went too far.
It definitely went too far.
But so that's levels of redundancy that like where one of the levels is not very sound, but adds a great deal of complexity, right? And so maybe we should put those together. But another thing about Unix that like, this is maybe getting more picky, but you know, one of the cool philosophical things was like, you know, file descriptors, right? Like, hey, this thing could be a file on disk, or I could be talking over the network. Isn't it so totally badass that those are both the same thing? And like in a nerd kind of way, like, sure, that's great. But actually when I'm writing software, I kind of need to know whether I'm talking over the network or to a file. And I'm going to do very different things in both of those cases.
Yeah.
And so I would actually like them to be different things because I want to know what things that I could do to one that I'm not allowed to do to another and so forth.
Yeah, and I am of such mixed mind because it's like it is a powerful abstraction when it works, and when it breaks badly.
Yeah, it's just I think it was more powerful when it was conceived, right? I think for the time, you know, 1970s, early 80s, I think that was probably the right thing, right? I don't think it's the right thing today. And the problem is nobody is willing to question things at that low of a level because I think they just perceive, A, it'll be way too much work to try to build a new thing from scratch that's not like other people's things. And then B, once I do that, nobody will use it. And so my life will be wasted, right? And the problem is we need people who are brave.
Yes.
We need people to go, we need like the 300 Spartans or whatever to go out and like do some things.
We need people crazy enough to start a computer company.
Yeah.
No, I think you're right. I think that we need people who are going to be courageous with respect to abstractions and understand also that you can work for an abstraction that may have limited utility, but that utility can be important. That can be an important subsection. I mean, it doesn't need to be everything to everybody. I think that, in fact, that era needs to end. I think that we've oscillated a couple of times into this where everything is going to be written in Java. And then we realize like, actually, shit, that's a bad idea. some things should be written in Java, but a lot of other things shouldn't be.
Yeah.
And right now, I think it's like we need to accept that different domains are going to have different, they're going to be expressed in different languages. They may have different systems, but it's not an excuse for this kind of spurious incompatibility.
So I would like to solve this. So, I didn't like Java when it came out. I never really programmed in it. But like, again, because the people who want to do their React applications kind of have a point, I would like to figure out, how do we actually solve that? Like, what is the most technically sound thing that we could do?
Yeah.
Where I could actually copy my program to another operating system. And let's say it's not magical. Like, let's say I even have to if-def around operating specific things and somehow that gets compiled into it, right? But like, then it runs, but it's like not as managed as Java, but maybe it maps to CPU instructions. Like if we did something like that, it would remove, and I'm not actually advocating this as I'm saying it. I'm just saying, like, nobody's really taking that seriously, that like maybe Java was not the right thing, but maybe something near proximal to Java would be tremendously better.
Yeah.
Would allow us to have something very low level. Like things change, right? So like being exactly optimal in terms of CPU instruction count is not that important, right? So like all this like worrying really hard about jitting something into an optimal thing, not actually going to get you that much mileage today, right? But like, oh, we've got some bytecode that we know is pretty close to ARM and pretty close to x86, and we could sort of like map it in the last stage. Is like, that's not the worst thing. I mean, I would prefer to ship something that I compiled directly, but like if that is what enables people to copy a program from one computer to another without having to have an installer and downloading dependencies and then have it like not work correctly anyway after all that, like we need to start thinking about that. We really do. And nobody is. And I don't know.
Well, I think that I do think, again, I think that it's these kind of problems from which are born great and revolutionary ideas. So I'm hoping that that JI, whatever, I'm hoping that's going to, close beta starts soon, but I'm hoping that's going to get out there.
I don't know what the timing for that will be. It's going to start small and it'll grow over time.
Yeah, that's great. I think that's terrific. This has been an amazing conversation.
I feel like there's so much we didn't say, but that's fine.
And so many more rants to be had.
Yeah.
But no, I think this has been great. Jonathon,
thanks for having me.
We cannot thank you enough. This has been so much fun. And it's so great to, I have to say, speak to someone who is not doing computing for its own sake, but actually really focused on delivering something to an end user is really terrific and refreshing, and yet still having that deep systems perspective.
It's so in the same way that having to code directly to metal, there's an element of reality there.
Yeah.
Caring what something looks like to the end user is like it's a different wall of the room of reality.
Yeah.
And like seeing both of those walls at once is useful, I think.
It's very useful.
Really?
And it's been a great conversation. Jonathon, thank you so much for joining us today.
Right on. Thank you.
All right. You've been listening to On the Metal, Tales from the Hardware Software Interface. For show notes, to learn more about our guests, or to sign up for our mailing list, visit us at onthemetal.fm. On the Metal is a production of Oxide Computer Company and is recorded in the Oxide Garage in Oakland, California. To learn more about Oxide, visit us at oxide.computer. On the Metal is hosted by me, Brian Cantrell, along with Jess Fursell, and we are frequently joined by our boss, Steve Tuck. Our original and awesome theme music is by JJ Wiesler at Pollen Music Group. You can learn more about JJ and Pollen at pollenmusicgroup.com. We are edited and produced by Chris Hill and his crew at HumblePod. From Jess, from Steve, from me, and from all of us at Oxide Computer Company, thanks for listening to On the Metal.